Good morning, all of you. Am I audible? Morning, sir. Am I audible? Dear participants, if am I audible, kindly write in your chat box. Okay, thank you.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning. Just relogging, okay? Hello, Dr. Juthika.
Yes, sir. It is feasible.
I'm just relogging, okay?
Yes, sir. We will start by 10, sir.
I will be relogging. Just a minute.
Yes, sir.
Okay, now it is coming. I'm just trying to make it. Just a minute. Kitty. Okay. 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 Whether I am visible there?
Sir, visible, sir.
Okay, I cannot see this screen.
Visible, sir.
Visible. Whether it is full screen?
Sir, now it is full screen.
Okay, okay. What is the background of the participant?
Sir, it is
Doctor?
interdisciplinary time. Some are from polymer, some are from chemistry, physics, mechanical, multidisciplinary.
At a multidisciplinary. Okay.
Science and
Faculties are
engineering background. Some are from
science and
chemical engineering also.
So how many faculties and how many research scholars are there?
Sir, we have more than, yesterday, more than 200 participants has attended the program. Most of them are, sir, faculties.
Most of them are faculty. So
Yes, sir. And fewer postgraduate and research students. And fewer from engineering students also, final year type.
okay.
So very warm good morning to Dr. Pike, sir.
Good morning all.
And offline, we have our HOD of training department, Deka sir, then Rotikanta sir, Debojit Kolita sir, and my dear students and all the participants who have joined. So today we have with us Dr. Pradeep Paik, sir, who is an associate professor at School of Biomedical Engineering at Indian Institute of Technology, BHU. Sir, area of interest is materials for healthcare and therapeutic applications, new designing and synthesis of polymers, ceramic composites, other nanoscale materials of healthcare and nanomedicine, implantable materials, drug delivery, cancer therapy, nanovaccination, in vitro and in vivo studies. Before joining IIT BHU, Sir was associated with University of Hyderabad as an associate professor. And before that, Sir has spent a couple of years in Israel and National University of Singapore. And he has tremendously contributed into the focused research area of the translational nanomedicine. And we are very fortunate enough that today we have with us Dr. Pradeep Paik, sir. Over to you, sir.
Thank you very much, Dr. Jutika. To you and your group. Okay, thanks a lot for inviting me. Now I will be sharing my slides. Okay. So good morning all. Is my slides is visible now?
Yes, sir.
Okay.
So it is not a slideshow view, sir. Mode.
It is slideshow mode, not coming?
Yes. Yes, sir.
It's moving. Am I correct? Whether slides is moving?
Yes, sir. Moving, sir.
Okay, fine. Okay, good morning all. Okay, good morning, Dr. Jutika, for and your team to invite me to tell about something. Okay, let's say your title of your talk is management of resources. Okay, recycling or like these things will be there. Okay, what about theme you have mentioned is that?
Yes, sir. Waste to wealth concept, plastic waste management.
Plastic waste management. Then I thought that what about I have done long back. It's like a procedure we have mentioned how we can manage these commodities thermoplastic materials. Okay, so whatever I will be telling, it is not the current research, but it's a very important which actually help us to come up to this point. So I'll not be talking much about today about the biological importance of these polymer materials, but those who would like to work on the management of the waste of the commodity thermoplastic materials, it will be helpful. Okay. So although I have mentioned nano, because we have started the work with how the commodity thermoplastic materials we can make nano and what is the other things will be there. Okay, let's say topic, what is that? Polymer nanoparticles and its stability and lifetime. So I will be talking about the mainly 3-4 thermoplastic commodity thermoplastic materials which make actually they are available from, let's say, downstream product of the petroleum industry. Okay, like polyethylene, polystyrene, polypropylene, like this. Okay, so how we have managed these things, and whenever we have made them into the nano, what is the property actually change and what is their lifetime? Okay, lifetime, what will be the lifetime, which will be helpful. Anyway, Dr. Jutika already discussed that we work on materials for healthcare and therapeutic applications. Actually, we do. Okay, we do polymer-based nanotechnology, delivery, modeling, designing, development of effective long-term delivery system. Okay, let's say medicine. And synthesizing new biodegradable polymers, delivery system, all other things will be there, which is related to this. We work on composites. So it's our group is interdisciplinary and so many areas, research scholars and collaborators work with us. Okay. So let's say what is our old research? Old research. This is not new actually. Whatever we will be discussing, this is our research only. How we manage. Let's say what is the background of this doing this work? The problem of this beside the synthesis of polymer nanosphere. How we have, let's say we have started the synthesis of the nanoparticles of polymers from the commodity thermoplastic materials in 2001. Okay, and what is the motive at that time? What is the problem was there? How we have synthesized? Okay, whenever we have after the processing, let's say whatever your waste will be there, if you process to reuse these things, okay, you need to do some characterization. Okay, and during the processing, what will be their stability? So you will be getting lot of idea. These are the basic study we have done, which actually help to the engineers, okay, and material scientists of various background, different background, to go further in the next step. Okay, so let's say start with some basics. Polymers, it's a long chain molecules. If we take the example of polyethylene, it's a ethylene, it can be various type. Okay, we can take polypropylene, polystyrene, all these things. So usually whatever the market available, these thermoplastic materials will be are available. They are very much high molecular weight. Okay, 10 to the power 5 to 10 to the power 6 atomic mass unit. Or you can design them low molecular weight, but low molecular weight, these thermoplastic materials are just like paste. Okay, let's say oligomers, close like oligomers are very like paste type of things. Okay, so nanopolymers or nanoparticles, whatever you can make, we can make them. We can process them actually. Okay, how we can process? We can make them dimensionally in various ways. X, Y, Z. If you take, okay, if you can make the real nano, you can say 100 nanometers, but any of the X, Y, Z can be varied. Okay, you can make one dimensional, you can make two dimensional, you can make three dimensional, fiber, film, or any type of particle shape you can give. Okay, so how we can make? You can make if you compare them, whatever their size. Okay, how you can compare? Let's say we have mentioned 100 nanometers, we can give the size. I will be telling what is the problem. We can make 100 nanometers of them, or what is the advantage. So atom diameter is 1 nanometer, below 1 nanometer. 1 nanometers, let's say not in the nanometer scale, 2 to 3 nanometers or 4 nanometers. Okay, DNA 2 nanometers, protein, virus, you see the scales are there. And materials available, okay, whatever synthesized materials, okay, fluorine, nanoparticles, quantum dot, they are in the bigger of size. Okay. Whenever we have started the work, or up to which point we have studied, let's say up to 2007, okay, the studies we have finished. Okay, after that we have shifted to the different area of these materials, how we can use the biological purpose. You see that the tremendous increase in the number of the publications, the number of patents. Okay, how tremendous increase. If you say initially, okay, 1990, how few number of publication was there. In 2008, how was almost 60,000 publication was there. Okay, so it's a very, if you make them, if you recycle them, okay, what about the thermoplastic materials available, we use, you recycle them for different purposes. A lot of things can be available and a lot of things can be generated for the use of the society. Okay, so how you can use them actually? What is the motivation of this? If you can make them in the size of the nanoscale, and if you would like to use them for biological purposes, what can be that? Polymer nanoparticles kill the tumors. Okay, polymer particles kill the tumors. Scrubbing of oil from the soil. Let's say a lot of oils are there in the soils. Okay, it is not like too much this oil, not like the reservoir. So what is that? You can make the sponge of these polymers, then you can soak the soil from the soil. Okay, and photodynamic therapy is related to the cancer therapy. Okay, you can use this part. You can separate off DNA. You can separate DNA. You can make membrane. Okay, you can separate them. Separate DNA. Enhance mechanical property. You can enhance the mechanical property if you reduce into the nanoscale or reduce size. Okay, polymer particle for light diffusion. What about the coating are there? Let's say on the surface of TV or somewhere else. Okay, some light. So they diffuse the light. Okay, they scatter the light and they increase the visibility in three-dimensional space. Okay, now else you can use. So metal coated polymer particles used as an anisotropic adhesive. Okay, so whatever your resource will be there, if you waste will be there, you can use them as a coating of the metals. Okay, so if you make the coating of this metal, then what will happen? You can protect them from the environment. Okay, for metals. Okay, non-metals. Okay, and many of the polymers, they are inert towards the chemical environment. So you can protect them. Calibration standard. If you make the smaller sizes of particles, they are very much used for the calibration standard. Okay, you can use them in photonic devices. You can use them, you can give the temperature responsive behavior to the polymers, and nowadays there is a lot of uses are there. Okay, so if you would like to manage the waste, your target can be various type, and you catch them, and lot of whatever, I'm 10, almost 10, 12, I have told the application, this can be focused. Okay, now how you can. So existing polymerization methods will be there. Okay, and you can make some waste. So if you would like to manage the waste, what will be there? You can reprecipitate them. Okay, you can make the suspension. You can disperse them in some solvent. You can use some secondary solvent. Okay, so from the bulk size, from the bulky size, let's say sub-micron size or micron size, you can reduce the size in the nanoscale. You can make powder. Okay, you can make powder for coating. You can make powder for coating of walls, kitchens. Okay, the non-adhesive type will be there. So precipitation, suspension, and dispersion will be very important. Okay, for the recycling of this polymer. Now, other methods are there: micro emulsion, mini emulsion, or other mini suspension. Lot of other methods are there. If you have the MAR unit, then you can get the polymers. Okay, and the nanoscale. Fine. Now see what the thumb rules you have to maintain. If you take the monomer, if you take the mass, okay, mass of the mass will be mass of the mass, not individual mass. Total mass of the mass will be controlling. If you increase the mass, then particle size increase. So keeping in mind whatever the molecular weight of the polymers, whatever you will be recycling. Okay, based on that, how will be your nano size? Okay, droplet size, stabilizer concentration, solution stabilizer. Okay, how you are giving the stirring speed if you recycle them in the solvent. Okay, polymerization rate, continuous phase if you do the polymerization. Okay, if you use secondary solvent, then you have to keep in mind whether you will be using the secondary solvent to make the secondary phase. So by heating of the polymers, only you can get the in the bulky size. But if you use this secondary solvent, along with a primary solvent, then you can give a different size. So what the advantage you will getting that whenever you will be using solvent, whenever you will be using a secondary solvent, that cases whatever the impurity will be there, okay, in these leads, recycled materials, that easily can be removed. Okay. So you have to keep in mind, okay, what is the stage, whether they are in oligomer state or they are polymer stage, or where they are, what the molecular weight they are like. So you have to keep in mind. So all these things will be as a take-home message, those who would like to do the recycling of this. Okay, by nanoparticles, let's say I have told that we have made it for the polypropylene, polyethylene, and polystyrene. Okay, why we make it? Composite and powder technology, if you would like to make the composite on powder, then what happens? Easily you can get bulk, but for the composite making, you have to make the uniform distribution of the filler materials in the matrix. Okay. So bulk materials mixing in the filler materials is very tough. Okay. Then what will happen? You make powder. You make powder of these commodity thermoplastic materials and try to give the filler. Let's say you wanted to give the polymer filler in the rubbery materials. Okay. Then it's very difficult to mix. Okay. If you make powder, then you can have the easy accessibility to make them uniform mixture. Okay. Bio and food technology cases, you can easily make the film. Membrane technology, you can use membrane, waste water treatment. You can make membrane, you can functionalize them. Okay, you can use them. You can make the coating, you can make the packing, you can so many uses, whatever I have to. So we thought that, okay, let's do it like this. Okay. So let's say what problem we decide that time. Okay, synthesis of nanopolymers. Polypropylene, polyethylene, polystyrene, I will be telling. They are very high molecular weight. Achieving the nanosize of them are very tough. Until unless you separate the single molecular chain from the bulk, from your waste, okay, from your waste, bulky materials, whatever in the environment available here and there, okay, it will be very difficult to make them the nanosize until unless you are separating single molecular chain, okay. So main drawback is high molecular weight, okay. So whatever we have done, so long chain, they will have the van der Waals forces of interaction among the chains, and you will facing difficulties to separate the single molecular chain. Okay. Particle size distribution. Whenever you will make the particles, particle size depend on physical properties. Okay. You will see crystal structure will be changing. Amorphous to semi-crystalline, crystalline, so many things will be there. So during the processing of them, you will have the different structure. By recycling so many times, by heating and cooling of the thermoplastic materials, the chain will be rearranged. So according to the rearrangement of the chains, either they will be amorphous, or they will be semi-crystalline, or they will be crystalline. So repeatedly, how you are processing them. Okay, though that you have to keep in mind. Particle size dependent thermal properties we have studied. Okay, I am showing. They will be changing. They will be changing glass transition temperature, melting, softening, and percentage of crystallinity, which actually control up to a certain extent the mechanical property and thermal stability. We will be showing this. I will be showing the hot result. Okay. Particle size dependent surface property will be there because the molecular folding of the chains will be changing. Changing of the molecular chain folding on the surface of the nanostructure will be changing. So we'll be saying establishment of the nucleation and grain growth mechanism. You can explain by this. Okay, you can explain by the how the nucleation and grain growth during the processing of them. Okay, from the bulk nano, that you can. Now, other stability is the mechanical stability. I come to know that many of you are from the mechanical background, but whenever they will be in the molecular chain, single molecular chain, how their mechanical property also changing, will be showing. Okay, for that reason, we will be showing that fabrication of FMT, we have fabricated single molecular chain mechanical property we have measured. We will be showing a model developed modulus of long Z direction we have measured, And we have used that the mechanics, contact mechanics to find out the mechanical property of the single molecular chain. Okay, so you all can do it. You will get a lot of homework, take home assignment with this. So lot of things you will be getting. First, whatever I have told, we will be discussing the lifetime. So whenever you will be processing, okay, into from the bulky to the nano, how the lifetime will be changing. Degradation behavior will be changing. That will be showing. Okay, it will be very interesting. Okay, so you can, let's say, materials, method, those who are the polymer backgrounds or chemistry background, you know that you need some precursor materials to synthesize, okay, medium, solvent, okay. And if you use the polyethylene and polypropylene, okay, if you design them, if the polymers prepare from the mud, then we'll have something. You have to use catalyst. And most of the cases, it has found that catalyst can be the impurity during this method. Okay, catalyst, metal catalyst, okay, magnesium chloride or some other type of catalyst, titanium chloride, trimethyl aluminum, and dimethyl siloxane. All these type of weight are used to hold the catalyst. Okay, so that there is chances of this can be the, okay, this can be the impurities. Okay, so easiest way to synthesize is the polystyrene. We have synthesized and we will be showing you how these nanoscale things changing. So okay, so this is the method has been given as a Grignard reagent FBG used, where we have used polypropylene synthesized and polyethylene. Okay, so you have to take then reaction chamber, you have to do reaction around the 160-degree temperature. Okay, all the method with changing this precursor, you will be, okay, you will be getting the polyethylene and polypropylene ethylene. Then you have to treat with the acid to remove the, let's say, catalyst. Okay, and then you have to wash with water. Now you have to think whether you will be using methanol or ethanol or something. Okay, something alcoholic thing. Okay, to dry it. So you have to keep in mind, if you would like to use them for any biological purposes, using of methanol is not advisable. Okay, because methanol are toxic. Okay, methanol are toxic. So polyethylene treated with common solvent and allowed to preparation in different solvent will give you the different sizes of particles. Okay, that will be there. So there will be a lot of mechanism. Don't forget about the mechanism is there. So whenever you will be using the catalyst particles, okay, on the surface of the catalyst, the polymer chain will be deposited. Okay, you see like this, and then they will be like assembled. They will be self-assembled or gather or coagulate. Okay, so why during inside the coagulation, the catalyst will be there. So why it is required to remove the catalyst. Okay, catalyst particles will be in nano size or few atom size. Okay, so they will be there. So whenever you will be recycling, you have to keep in mind that lot of impurities will be there in the bulk materials. Okay, or if you collecting these polymer materials from the environment, okay, used for some other purposes. So you have to very much careful to wash them for using them. Okay, so whenever you will making them into nano, you can characterize them. Okay, so during the recycling, first step, what you can do Fourier transform infrared spectroscopy, which will give you the, whenever you will be treating them with chemicals or some heat or other type of treatment, their functional properties in terms of the chemical structure has been changed or not. Okay, in terms of the chemical structure, so that you can use the FTIR. It will give the functional group indication. Okay, the atomic force spectroscopy we have used two purposes: to check whether we are able to separate the single molecular chains or not, and whatever the mechanical property of the single molecular chain created during this recycling or reprocessing of them. Okay, then we can check them transmission electron microscopy. Okay, TM. Okay, scanning electron microscopy, how small or bigger size morphology has been generated. Okay, whenever we give the shape of the nano. Now, whatever I have telling that, okay, the property of the polymers will be changing lot with change in the crystal structure from amorphous, semi-crystalline or crystalline. Okay, that you can study is characterized by X-ray diffraction method. We can discuss, I can discuss all this method, but there is no scope. Only we'll be taking the example how they have changing. Okay, differential scaling calorimetry, you know. Okay, thermal stability, melting, glass tension temperature, recrystallization temperature, endothermic, exothermic, crystal recrystallization, new crystal formation, let's say alpha, beta, gamma. Okay, polymers are mostly the distorted type of crystal structure. Okay, not the cubic or simple cubic type. So hexagonal, triclinic, rhombohedral, this type of, okay, where there is less symmetry. So this type of crystal structure will be forming. Measurement of mechanical property will be showing AFM how we have used. Then thermogravimetry analysis. Quickly, the processing method I have told. Okay, for FTIR you make the film. Okay, you can check. For AFM, ACM, TM, you can make the powder of them, disperse them in alcohol, dry them, and you can do. For XRD, you take powder, solid state crystal structure. You can do study, or you can do them film. Okay, to study the crystal structure. TGA, DSC, you can take film, powder, okay, everything. AFM, you can take film, powder, everything. So how you will be studying these things? Okay, some results, let's say. So solvent processing. Okay, if you use the solvent, let's say you will have the option. I have given some option: acetate, acetic acid, propanol, ethyl acetate, toluene. Okay, you can use the concentration. Polymer concentration you can use, let's say, very low to high. You can use the RPM 1000, 2000, 3000. I'll be telling, if you increase the RPM, what can be happened. Okay, actually, okay, you cannot get the separate particle. Actually, I will be showing. Let's say temperature. If you increase the temperature, polymer are thermally less stable. Although polyethylene, polypropylene, polystyrene, polyethylene around 126, polypropylene around 165, 66, or polystyrene 236, the thermal stability. But still, if you use low temperature, there is a less chance of degradation, okay, of the polymer change. Okay, so processing temperature you can maintain. But if you use them in some solvent, okay, it can be easily, you can process them in temperature. Now you see this. When RPM was, let's say, you can maintain, okay, 1000 in some acetic acid concentration, you see the morphology you can get. You can get morphology. So if the 5 micron size is there, you see ununiform sizes of particle. Here, the processing temperature in the solvent was 40 degrees centigrade, okay, in acetic acid. Fine. Let's say if you use the ethyl acetate, okay, RPM same, concentration same, very low concentration we have taken, temperature same, only change these ethyl acetate solvent. Now you see that how the coagulation happen of this particle, okay, how the coagulation happen, the bigger sizes of particle, okay. So this type of possibility will be there. So you have to keep in mind how you'll be doing. But toluene, these thermoplastic materials, polyethylene, polypropylene, if you take them in the toluene and heat them, actually, initially you have to heat it around boiling temperature of toluene is 80 degree, then you can slowly decrease. So you can get the uniform sizes of particle, which will be a spherical inside. Okay, you see this, all the particle, again I will be showing you the clear structure. Okay, this is the AP same result, normal same result. Okay, we are able to do it around, let's say, 2003 or 4. There was no concept of the HR same or HR temp, or in our country it was very rare. Okay, so that cases around night 3 o'clock we have, where there was less stability of the environmental stability was much more, vibration was not there for electron beam. Around night 3 o'clock we have just able to acquire this type of images of these polymers. Okay, how this spherical. Now again, the solvent. For this, you can achieve lower sizes of particle. You see, you reduce the temperature, concentration, okay, everything. You see that the scale is 200 nanometers and the particle size will be around 60 to 100 nanometers, 200 nanometers. Okay, so polymers, these thermoplastic polymers and high molecular weight, but still you can achieve this nano size. Okay, so nano size you can achieve because you will be able to separate the single molecular chain, only one molecular chain which is helping to form the particles. Okay, They will helping you. I will be showing you also the molecular weight where we have done the thermal treatment, press you have used the starting other things, but still we are achieved to maintain the high molecular weight, because high molecular weight will be advantages to achieve the mechanical property of stability. Okay. So variable concentration, okay, you can use like this. Let's say I have given from 0.0025% to 5% or whatever is there. So you can do these things. So you will be getting the different concentration with different concentration. You see, with decrease in the concentration, particle size will be decreased. Okay, you see that it is close to 100 and it is going 200, it's going 400. Similar phenomenon will be achieved in the temperature also. Okay, now see okay, sample you see different concentration. Okay, you see particle size 35 to 300 nanometer when it was the very low concentration, and almost micron size particle. You see the micron size of particles we achieved. I will be showing. Okay, and whenever the concentration was very high. How the shape and morphology change for this particle? Whenever they are smaller the size, okay, you will be achieving spherical sizes of particle. But whenever you will be increasing the size, concentration, they will be non-spherical, non-uniform. They will be like a coagulation. Okay, above 1% of concentration, they lose their spherical identity. Okay, they will be like a uneven shapes. Okay, now see. So process standardization you can make where you see the solvent propanol, temperature 40 degree, concentration, this will be their RPM variable. Up to the previous slides, okay, we have mentioned that RPM was fixed. Okay, temperature varied or solvent, different solvent varied. Now you see that if you varied the RPM, okay, I was telling from 500 to 1000, I was telling with RPM, change in the RPM, how it will be there. You see that with change in the RPM, size, morphology, everything will be changing. Their population also will be changing, because if you increase the RPM, the particles will be collide to each other. Particles will be collide to each other and will be fusing after critical RPM. After critical RPM, and you will not be able to separate the particles, and other things will be there. Entanglement of the chains will be increasing. Okay, so entanglement of the chains will be increasing, and the particle size also will be increasing. So here we have shown up to the 100. Okay, so relation will be changing. Now you see, so whenever RPM was 50 to 50, 500, 1000, this was there. So particle size, let's say at low RPM, 75 to 600, but we changing these things. Okay, population will be changing this. Maximum particle size, let's say the lower 69%, 50 RPM, 150 nanometer size. Okay, 590, 1000, 100. Again, when you increase the RPM, okay, particle size increase. This is only due to the coagulation and fusing of the particles. Okay. So 500 to 1000 give the best results to get the spherical types of particles if you are using thermoplastic materials. Okay, let's say another things is there, variation in temperature. You see, so beautiful type of particle. So one example only, 0 degree centigrade temperature. Okay, 15 degree temperature, 50 degree temperature, so different processing time. 0 degree temperature means we have tried to separate it where the solvent, this was soluble in some solvent, okay, in high pressure or something, and we mixed in even a secondary solvent where the secondary solvent temperature was, okay, 0 degree centigrade. So what we have done, we have first made it soluble in some solvent, let's say xylene or toluene. Then we put them in a secondary solvent where the secondary solvent temperature was 0 degree or 15 degree or 30 degree. Okay, so you see this population of the particles will be changing. Now let's say what is the temperature again? 45, 60 degree, 75 degree. You see that when 60 degree temperature was there, almost the particles was the spherical in shape. Okay, you see spherical. But again, if you increase further the temperature, so you will see that Again, you can achieve the smaller sizes of particle, but we are not sure that they are spherical or something else. Okay, they have specific shape. Fine. So what is telling? So temperature of the secondary solvent 0 degree, 75 degree. Where spherical achievements will be there. Particle size 100 to 50 particle size around 60 degree centigrade. All other cases non-spherical is there because they are arrested. Their movement of the change arrested somehow. Okay, and in the 60 degree temperature, the movement free, whenever they will, okay, temperature collapse will be there, they can shape the spherical shape. Fine. So these also we studied that you can arrange them in the proper way. You see that. If you see that this is an AFM image have been shown, and you can arrange these particles in single hexagonal. So they can be separated from each other. You see? So hexagonal elements, almost their distance from the center particles will be you see that almost same. 1, 2, 3, 4, 5, 6. 6 particles are there. So you can arrange them. You can give the self-assembly shape of this type of particles. Okay, you see further how the polypropylene. So this is the camera image have been taken, not this electronic camera. So flash camera image we have taken long back. Okay, so the particles are separated. Now you see surface morphology of the polyethylene particles how can be. Okay, in that this is 3-dimensional space and the particle size, how we can generate them. Okay, how you can arrange them in the film. Okay, you see this particle 3-dimensional space. So they are comparable of these things. We have studied them in different characterization tools to check how they are separated. Now you see these particles of polyethylene, how they are separated. So you can achieve them. Okay, even 50 nanometer sizes of particle. Question obvious will be there. So their molecular weight, let's say 10 to the power 5 to 10 to the power 6, but how we are achieving? So if you see, if you do the literature, then if you do some molecular dynamic simulation or some MD simulation, you will find that even a 10 to the power 6 AMU molecular weight, if you can compact them, the Z value, radius of rise, and even you can get the 9 nanometer to 10 nanometer size. Okay, a polymer of 10 to the power 6 molecular weight, if the radius of gyration, if you calculate in MD, okay, then you will get the radius of gyration will be almost 9 to 10 nanometers. So achieving 50 nanometers, it is not wrong. Okay, if you can separate and they are very much compact inside these particles. Okay, inside these particles, so you can achieve these smaller sizes of particles of the thermoplastic methods also. Okay. So conclusion, what can be drawn if you process them? So process has been standardized. You can standardize them according to your achievement. Below concentration of 2 nanoparticles of polymers you can achieve. RPM you can maintain 500 to 1000. So give nanoparticles with spherical shape. Shape anisotropy of polymer particles obtained when process temperature kept in the range 45 to 60 degree temperature. So you can achieve them. Okay. Let's say for the polystyrene, actually we achieve the nano size. So easily available benzoyl oxide, okay, sodium lauryl sulfate you can use. This is surfactant, and use the styrene. You increase this temperature. Volume of the reaction you maintain whatever you want. According to the volume, particle size you will be changing. Polymerization you will doing 70 degree. Magnetic stirrer use 4 for 5 hours. Series of reaction you can perform. Series of processing you can perform to get the different sizes of particles. Now you see how the spherical shape, complete smooth surface of the particles you can achieve. Okay, for this polystyrene. So they will be completely compact. You see that how these particles. I will be showing again. Okay, see how the beautiful sizes of particles. Okay, and particle size you see that almost 46 nanometer. There we will be showing again 46 nanometer sizes of particles you will be getting. So if you see this is the particle, single molecular chain polymer chain polymer particle for polystyrene. If you see that all the particles are almost 20 to 40 nanometers in this range. Okay, so they are very much compact. I will be showing they are very much compact. Okay, so conclusion, you can characterize them. Okay, let's say here nanoparticles of polymers are spherical. You can make same FM, all everything will be. If you are doing, then they will have a good agreement whatever you have done. You can characterize them. You can characterize them. Okay, through the let's say FTIR. I have shown different thermoplastic materials. They have almost three polypropylene, polystyrene, all these things, and they don't have any change. They don't have any chemical structure. They are almost giving the same spectra. Okay, it means that whenever we process them, we have processed them, there was no change in the chemical structure. So if you maintaining a proper solvent, if you maintaining a proper temperature, if you maintaining a proper environment also, okay, then what will happen? So they can have the identity remain the same, chemical structure will be remaining same. Now very interesting things I'll be telling about the crystal structure. Whenever you reprocess, okay, let's say we compare the crystal structure, crystallinity, everything. Here giving the examples for the polypropylene. So you see, we have used polypropylene of the size, different sizes we have made. Okay, we have reprocessed into different size, 20 micron, 10 micron, 5 micron, 1 micron, and 50. So if you see from this figure A, you will not understand. If you go to the figure B, if you see that the width different in this size, okay, when the particle size are smaller, okay, their crystallinity increase. Okay, so what happened that whenever we have reprocessed them, okay, you see in every cases you see that intensity of every peak, okay, and particular crystalline peak, let's say for 040 it is for alpha, okay, 130 this is for the alpha, okay, and all other things 11 alpha, 301 this crystalline peaks, the intensity increased. It means that what is happening? The rearrangement crystallization occurring. Okay, the right side also. So we have published this thing. So what happened that? So when the intensity becoming sharp, peak becomes sharp, it means that it is transferring from the amorphous to the crystalline, towards crystalline. Or you can tell if it is a mesomorphic, if it is semi-crystalline, so crystalline it is transferring from the amorphous to the crystalline phase, although it is not reaching to the 100% crystallinity. So some percentage of crystallinity will be increased if your processing is there. Now you see that polypropylene. According to the crystalline peaks we have calculated, okay, what we have calculated, particular crystalline peaks which is responsible for, let's say, alpha structure, okay, and then particular diffraction peak where it has come, and for what reason? When the diffraction peak are there, difference intensity, the distance between the two arrangement, the layer of the crystals are different, they will be changing. And if you see that, what is this? Spheruloid, okay? If you do these things, Bragg's equation, okay, the crystalline length also will be changing. Now we have calculated the percentage of crystallinity, okay? NM also is there, okay? How much, let's say, number of chain or how the entanglement, other things will be there. That also we have calculated. And crystallinity, in the crystallinity, how much is changing? Let's say whenever PP of these particles 20 micron was there, okay, crystallinity was almost 59% after the processing. But after processing, whenever the particle size was there, okay, 500 nanometer, less than 500, crystallinity increased up to 76%. So almost 16-70% crystallinity increase. What is meaning of the increase in the crystallinity? I will be telling you. Similar phenomena we have checked from the BSc also. Okay, so what happened that? So this type, whenever we have done the DSC, we found that almost 2.5 degree increase in the melting temperature. Okay, because arresting of the change. Because if we look after to our textbook knowledge, the amorphous nature of the thermoplastic polymers is responsible for the glastanation. Crystalline nature is responsible for the melting and mechanical property. Okay, so it means that there will be some changes. Okay, if you see 162, it's changing to 164 or 163. Okay, 60.5. So these many changes are there, melting temperature. So increasing. If you use this inside this body temperature will be 37.4 degree. Okay, means almost 98 degree centigrade. If your body temperature is 101 degree centigrade, it means that there will be 3 degree Fahrenheit, then 3 degree increase in the centigrade. Okay, almost 3 degree. So body temperature, body unstable will be there. So this increase in almost, if you see that, although it is 2.5 degree increase, but if you use this 2.5 degree increase inside this body, if you use this for biological purposes, it has lot of impact, okay, inside this body. So polypropylene crystallinity also increased 54 to 74, which we have studied this thing. So various. In case of polyethylene also, we have checked. You see that in case of polyethylene, okay, how much increase are there? If you see that almost 50% increase in the intensity for it, okay, whenever it is below 500 nanometers, you see the how much intensity increase. Almost increase in the intensity with respect to the 10 micron to 20 micron, from 10 to 20 micron to 500 nanometers of the size of particle. During processing, the crystal structure, crystal rearrangement. Actually, what's happened? There will be a rearrangement of the crystal, rearrangement of the chain. They can be organized. So the way we have processed, we have improved this property. Okay. So in these cases also, you see from the macro to nano size, okay, you can include some sort of crystallinity. Okay. So with increase in the crystallinity, okay, some thermal stability also will be increased. You see that heat flow behavior changing, shifting of melting temperature, let's say from 126 degree centigrade to 132 degree centigrade. Okay, so when they are in the crystals, it means that there will be acting the van der Waals forces of interaction much more. Okay, when they are arranged, much more arranged. Polymer chains are much more arranged. Now, so polystyrene cases also we have seen these things. Now, conclusion from the XRD and DSC for the reprocessing, polymers are more crystalline, nanopolymer. So you can make them whenever you will be making nano size of them if chains are properly arranged. In that cases only crystallinity will be increased. Crystallinity and crystalline length depend on the particle size. You have to keep in mind, and on that crystallinity and crystalline size, how the mechanical property will be developed, that will be depend. Crystallinity increase with the decrease in the particle size. It is depend on how you are processing. Okay, if your processing is different, processing method is different, then that all the parameter can be changed. Now you see. So surface morphology you can change. Surface morphology are very much important if you use these things for biological purposes, because bones and other things, whatever if you would like to make artificial bone, composite, you have to make the rough surface, so that on the rough surface cell can grow. Now you see, so whenever there is a particles we have processed around 40 nanometers, the roughness is very less. Whenever increase the particle size, you see surface teeth height increase. Okay, why the surface teeth height are increased? This happens because so many chains deposited to each other, they coagulate, they agglomerate and form the bigger sizes of particles. So the impression of this surface teeth height is the indirect message giving that the chains are folding in such a way. Okay, these are smaller smaller particle deposited on the surface of the nanoparticle. You can see that smaller particles are very much visible on the surface. Okay, so these are the height of the smaller particles, or almost the diameter. If you draw an imaginary sphere of this, you can get the diameter. But in case of nano sizes of particles, whatever the surface roughness are coming, that roughness generated only due to the chain folding, not the deposition of particles. If it is a single molecular chain, there is a folding of chains will be there. Okay, or small entanglements will be there, small folding. It's like a small loop will be there of the chains. Okay, so you see that quantitatively we have measured the mean roughness, RMS value. Okay, root mean square roughness value. Okay, so whenever particle size are 40 nanometers, we have done these things. How we have calculated? We have calculated these things from the AFM, atomic force microscopy. We have measured this. We have calculated the chain folding, roughness, average roughness, mean deviation of roughness, maximum peak height. Okay, whatever will be there, I will be showing. Minimum depth, okay, RP value, height of oil and height of the peak. Okay. So RMS value, we have found that whenever particle size we have reduced up to 40 nanometers, roughness is 6.38 angstrom. So this roughness is only due to the atomic scale folding. Okay, 2-3 atoms are chain in the chain, they have make loop. But whenever we increase the 500 nanometer size of particles, you see that 77.72 increase up to from 6. It is means that a loop of chain, like a tag. So polymer chain is like a tag. So they have coiled. Okay. So due to the coiling, it's happened. You see that. Oh, I have. Oh, it had. This is the surface roughness profile actually. Okay. You see what's happened there. Whenever more smaller sizes of particles. Okay. Whenever they assemble, initially I have shown that how the smaller particles assemble to each other. Assemble, make the bigger size particles. Then they allow further to deposition of polymer chains on it. So why whenever bigger sizes of particles are there, first happen smaller sizes particle assemble, then on this assemble layer of layer deposition of polymer chains will be there. Okay, then it will make the smooth surface. Now you see, so if you see this, so initially the roughness was there, then in middle cases polymer chain when deposited, then almost roughness are same. But again when once smooth surface form, and again the second cases deposition of the chains will be there. Then again, this due to the deposition of particles or much more chain folding on the surface, they will be creating more roughness. Okay. Now you see this glass transition temperature, how it can vary during the processing. First say what is this will be there for polypropylene. Usual glass transition temperature for macro size minus 25 degrees centigrade. Okay. So whenever you have reduced the size, how we can change these things? It has been changed to minus 11 degrees centigrade. Okay. So glass transition temperature, you see minus 25 degrees centigrade, minus 11 degrees centigrade. Okay. During the reprocessing, it can change. So reprocessing change the glass transition temperature. Glass transition temperature, it will give the first indication at what temperature and which range of temperature you can reprocess your polymers. Okay. See polyethylene, let's say minus 124 degrees centigrade to these things to minus 115 degrees centigrade. Okay, in this region. Oh, one extra one is there actually. Okay, so it will not be like this. So 18 in this region. If you see the polystyrene or polystyrene, usually you will get the glass transition temperature around 106 degrees centigrade, but the commercially available whatever we have tested, what was almost 90 degree, but whenever we have made into the nano, we have get it 106 degree. So almost 16 degree increase in the glass transition temperature. So glass transition temperatures depend on the particle size. You have to keep in mind the glass transition temperature depend on particle size, molecular chain. Okay, again it's depend on the chain arrangement also. I am going to show you. So what happened? What is the thermodynamical parameters is there? Kinetics associated with these things, all this theory of glass transition temperature. If we consider the film, decrease in film thickness and density will decrease the glass transition temperature. Decrease in the chain entanglement, okay, if chain entanglement decrease, then it will be easily move. It will easily flow on the surface. Chain will flow easily on the surface. And that cases, glass transition will be decreased. Enhanced mobility of the surface layer will decrease the glass transition temperature. Keep in mind. So whenever, if we go to our previous slide, whenever smaller sizes of particles, in which cases TG will be increased. Increase in the density, increase in the entanglement, increase in the decrease in the number of chain end on the surface. Okay, if they are entangled inside this spherical shape, then movement will be restricted. Okay, enhanced mobility of the surface will be decreased, or mobility of the surface layer will be of the polymer chain will decreased if they are properly compact. This only can be possible when, okay, crystallinity is increased. Okay, crystallinity increase means much more they are restricted. they are arranged. Okay, they are arranged. Much more van der Waals forces of interaction or other forces of interaction will be working, okay, to arrange them. Fine. What happen in these nanox cases also? If you increase in make the correlation with the entropy, okay, this is entropy formula. Some theoretical formula is there. Let's say C is the specific heat, T temperature, Gp for polymer particles, glass transition temperature, and Gb glass transition temperature for the bulk, which is again associated with the entropy of the bulk. Okay, entropy, okay, associated with the glass transition temperature, the particles. Okay, you see that if the entropy increased, then what will happen? Entropy increase means movement. The unrest things will be there. Okay, then unrest will be there. So if entropy increase, then what will happen? Gas transition temperature will be varied. Okay, gas temperature will be varied. Okay, gas temperature increase, it means entropy will be decreased. They will be much more stable, restricted. Okay, which is again related to the degree of polymerization, Boltzmann constant. Okay, and this is 5/3. Okay, or 3/5/3 respectively, are some constant value will be there, which is related to the specific heat. Okay, so by this formula, you can easily correlate what can be the reason for increase the glass transition temperature, okay, of these nanoparticles of polymer when it has been reprocessed. Okay, so reprocessing will be giving the much more higher property based on the how you are reprocessing. Conclusion: lowering of configuration entropy will increase the glass transition temperature. Okay, and will increase the melting temperature also. Now, why TG increase? What happened? So density will be increased, chain entanglement will be increased, chain ends on the surface will be decreased, and of surface layer, enhanced mobility of the surface layer will be decreased, and so why entropy will be decreased of the polymer chains and glass transition temperature will be increased. Now see, mechanical property. Now come to the mechanical property. So it is not very much easy to make the to find out the mechanical properties of the single chain polymer particles or polymer nanoparticles, although it is very easy to make the to find out the mechanical property of a thin film. Okay, it is very easy. By thin film you can make a thick film, you can use DMA or some mechanical analyzer, some instrument will be there. Okay, 3-point bending method, okay, whatever is that. But whenever your particle is, okay, nanometer size, how you'll be making the nanopart, how you'll be finding out these mechanical properties of this particle. Okay, so to measure this mechanical property, we have designed some model. Okay, what we have designed for the atomic force microscope. Right, what we have done, we have made this tungsten tip by focused ion beam. We have made tungsten tip by focused ion beam. Okay, so let's say it's a cantilever. On the cantilever, at the middle of the cantilever, you see that we have made this point. What is this point? It's a top view. Okay, you see the height of this is almost, okay, 50 nanometer, more than some micron, 12.32 micron height. And whatever the hemispherical top are there, okay, 50 nanometer, we have tried to take these restricted diameters of the if is 50 nanometers. Then we have taken the images. Okay, and similar type of images you have got. So we have not purchased. You will get the tungsten tip, FM tip in the market. Okay, but it's actually what happened is that, okay, so if you are not making FM tip properly, then what will happen? If you are not making FM tip properly, hello, हाँ मैं क्लास में हूँ ना, कॉल बैक करता हूँ. हाँ 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 हाँ, क्यों नहीं लग रहा? ठीक है, मैं 11:30 आपसे मिलता हूँ. ठीक है, ओके ओके ओके. So what happened? We have made the FM tip. I am very sorry, there was an important phone call. Okay, FM tip, we have made it. Okay, now what happened? We have modeled it. FM tip like a cantilever, it will behave like a spring. Okay, like this spring. Okay, then what is happening? What's happened that AFM tip will move down. We can make the compressive modulus. Polymer also we have like a spring behavior will be there, which follow the Hooke's law to some extent. Okay. Then AFM tip also will be there, which will be cantilever. We can compress them. Okay. Two spring linear model before and two spring linear model after compression. Okay. Compression will be there. So AFM tip will be moving. Okay. Compression, vertical displacement from the piezo movement will be there. Delta S, a deflection will be there for the cantilever. Deflection will be there for the cantilever. Okay. Deflection of the cantilever will be there. F leads to the deformation delta H. Okay. Means how much is going inside these polymer particles. Delta Z, delta S. Okay. So difference will be there. The deflection due to the atomic deflection. Okay. And whatever you can assume that, okay, to follow the Hooke's law, case you will have a spring constant. Spring constant will be for both cases. The cantilever cases also will be there. And if your polymer we have chain, we have like a spring. So that will be there. So easily by this way, how much it is touching on the surface, how much it is touching on the surface of the polymers, that you can calculate it by normal, a simple geometrical method. Okay. So you can calculate it. So whenever this will be there, whenever you will be indent, what the value will be getting, you will be getting the delta S deflection, delta Z so movement, okay, and F nanonewton. Polymer chains are single chain. We assume that polymers are single chain particles, okay. So you have to use the nanonewton range, the load or piconewton range, okay, and delta H deflection you will measure. And another parameter you will be getting plots delta Z versus delta H. Now from this three plot, you measure three slopes. Okay, you can measure the three slopes. Delta S by delta Z, or like this, or F by delta Z, or delta Z by delta H. So why? What is the need? Why you will be making this? So there is a model, okay, where df delta H by dh is a movement, how much it is going inside this polymer chain, which is related to the a by pi per half into e star related to the composite elastic modulus. Okay, so what is the a is the surface area touch on the, or surface area of the tip touch on the surface of the polymer chains. Okay, that will be there. That you can, by the simple geometry you can calculate. So we have to have a value. Now E by E star is the composite elastic modulus, which is related to the Poisson ratio of the tip, Poisson ratio of the polymer particles. Okay, Poisson ratio of the tip you can get it. Poisson ratio of polymers you can take the same value of the bulk. Okay, and elastic modulus of the tip you will have, you will have with that, you can take for the bulk, let's say tungsten you can take, and easily, okay, you can get the EP value whenever you will have by this, from this elastic modulus of the polymer. So listen, so you will be getting the slope, you will be getting the A value, I is known, so elastic modulus of the composite system will be getting where the if and polymers will be working. So this value is there, E star value is there. So what is unknown? Whenever you will be changing the size of the particles, the EP value will be different. So EP value, how it will be different, that you can calculate with different sizes of particles. Okay. So for getting these things, you take the slope, you put in terms of the partial derivative. Okay, you put and you can give elastic modulus. So what you have to assume with this method, the particles are well dispersed, you have to well disperse and put on some substrate. Okay, they should be properly dried. Right? There should not be any force acting. Okay, just liquid and tip. There should not be acting any force. Okay, they should not act any force or due to the liquid. So it should be properly dried. Only the tip and particles, they will be properly dried. Sample should be scanned properly. Okay, in acoustic mode also you can do, but you should avoid. You have to dry. You do in the dry medium. Check that the particles were indeed distributed diversely on the substrate. The FM contact mode you have to use, not FM different mode you do there. Non-contact, contact mode is there. So your tip should touch to the particles. Okay, how it should be touch well, touch that also I will tell you. And on the scan under a low applied force. If you do not apply it the low force, then what will happen? Chain will break easily. So you have to check the modulus value, how it is changing, how it is arranged, how they are interacted, so that the surface of the particles does not deform. So it should not deform. So there will be plastic deformation or elastic deformation. Your limit of applying the force in the nanonewton or piconewton range, which only cover the Hooke's law, not the permanent deformation will be there. Okay, so elastic deformation. So you have to mention. So what you have to acquire, force and distance curve have to be taking a different low amplitude of loads and analyze to get the elastic modulus. Okay, you have to get the elastic modulus well. The polymer particles and the cantilever tip surface are free from the friction. Load applied normal to the common plane of constant tip and polymer particles is static load. The tip is stiff compared to the polymer particles. You have to compare. The tip polymer particles interacted force only produces the elastic deformation of the particles. Okay. The tip polymer particle interaction force only produce the elastic deformation of the polymer particles. So elastic limit up to the elastic limits. The adhesion and capillary force should not be there. You should not consider. You have to arrange your experiment in such a way that no adhesive force will be, no capillary force due to the moisture will be there. There are only electrostatic repulsive force and van der Waals forces acting between the tip and the soft polymer particle. So these are there. So now you see that a lot of things we have done: 200 nanometer, 500 particles, 50 particles, 370, polystyrene, polypropylene, some everything. Now you see that we change in the particle size. Okay, how the elastic modulus value, gigapascal, you will be getting. Okay, from 1.3 to 1.5, or let's say 2.8, 2.5, it will be changing. Okay, so elastic modulus average value will be changing, let's say from the 1.32 to 1.14, depending on the particle size and their arrangement. Similar things, okay, also happen. Similar things also obtained for the polyethylene also. You see that we change in the particle size, their elastic modulus, indentation depth will be different because crystallinity will be different, hardness will be different. Okay, indentation depth, delta H value will be different, and elastic modulus value also will be different. So whatever reprocessing, after reprocessing, whatever you will be getting, okay, that will be changing. Now see polystyrene cases. Polystyrene cases, you see that it's coming like U curve. It means that lot of arrangement, rearrangement, deformation, things can be happen due to the phenyl ring are there. Okay, in the polystyrene, due to the presence of phenyl ring. Okay, based on the change in this. Okay, change based on the change of this. The arrangement, based on the arrangement of the polymer change, the mechanical property will be changing. Okay, now see, we have used this self-made FM tip. So it has been shown the commercially available FM tip. You see the tip size, okay, very sharp. Whenever you interact in the contact mode, actually it's break. Okay, but whatever the model usually used to calculate the elastic modulus, okay, so the hemispherical in nature is there. Otherwise, you will not able to use the Hertzian contact mechanics. Okay, whatever the primary assumption was there to find out the composite elastic modulus. And whatever the market available is there, they are silicon nitride based. Okay, whenever it will be used repeatedly, then they oxidize and their tip shape deform. And other cases is found that colloidal particles you can use on the cantilever tip, which it can be the spherical, but after the repeated use, they can be deformed. Okay, so they can be deformed. So why hemispherical you can use? Okay, now very quickly in 10 minutes I'll be finishing these things. Okay, 10-15 minutes. Okay, the TGA kinetics and thermal stability and lifetime. How the lifetime change? Okay, whenever you will be reprocessing. So there will be a various method. Okay, Friedman method, Freeman-Carroll techniques will be there. Okay, single heating rate technique and three heating rate technique will be there. And d alpha by dt, change in this mass with temperature or small time will be there. Okay, and degradation, how much will be there? Elastic EA will be activation energy, the degradation, which is related to the Boltzmann constant and temperature. So a lot of formula will be there, lot of model will be there. The Freeman, Carroll, similar type of model will be there. At 11, you have to plot this plot. So after doing the TGA, after doing the thermogravimetric analysis, you can get all these values. So Freeman method, Freeman-Carroll mathematical models will be there. Then Chang technique, one more will be their model. Okay, second Kissinger techniques will be there. Okay, kinetics model, all are these things is there. So second Kissinger technique where the multiple degradation peak will be there, like a composite polymers. Okay, two type of polymers making the composite. So that will be there. And another will be the cost rate form method also will be there. So all the importance, this importance model are based on the Arrhenius equation. Okay, based on the Arrhenius equation, which is related to the activation energy of the degradation. Okay, so that's a lot of methods are there, and another one is first Kissinger, then Tim Park method. Most important method we can calculate the lifetime of the polymers is that the fine wall method. Or we have to have this equation where ln q is the heating rate, q is the heating rate, ln z is related to the diffusion of the gas after degradation. Whatever the product will be generated after the degradation of the polymers. Okay, so activation energy will be there, alpha related to the change in the mass in the consecutive 2 points. Okay, let's say you have first calculating the degradation at 10 degree and or let's say 50 degree and then 51 degree. So that will be there. Alpha is related to the change in the degradation in 2 different points. Fine. So you have to take, let's say 5 degree heating rate, 10 degree heating rate, 15 degree heating rate. You can put this with this. Okay, you can calculate since RT is related with this. Then with that you have to plot. We have to plot these things. Okay, and then you can get lifetime. Now you see that. So estimation of lifetime based on the TOF model is there. So lifetime TF is estimation of lifetime of failure. Okay, by this equation you can calculate. Okay, PFX is the function and its value depends on the activation of the failure temperature T. Okay, now see. So you will be getting lot of these TGA plots where you can plot weight loss versus temperature. Okay, now you see this. So whenever heating rate at 5 degrees centigrade, 10 degrees centigrade, 15 degrees centigrade, if you check 20 micron, so stability increased, or let's say degradation will be increased from 540 degrees centigrade to 446 to 467. So it will be depend on the heating rate also, how it will be degrade. Okay, and you see the change in the particle size from 446 to 455. Degradation at 5 degrees centigrade will be different with change in the particle size. Okay, so degradation will be there. Rate of degradation will be there in different temperature also. So how will we increase the temperature during the processing? That also is very important. Now see. So you'll be getting, let's say, Friedman method. You can get from where you can get the slope. Okay, lot of study will be there, which is different particle size, micron size. This is for nano size, similar type of particles. Now we see that kinetics result, what it is saying, degradation kinetics. So let's say for polypropylene, or whenever the particle size was 20 micron, the degradation, okay, order of degradation was 12. Okay, almost 12. Whenever 10, it was 9. Whenever 5 micron, it was 8. Whenever, okay, again 500 and below 500 nanometer, again degradation. Okay, order of degradation increased. Okay, that's also varied with change in the temperature, heating rate. Okay, so this is there. And activation energy. If you see the activation energy, for degradation from 20 micron sizes particle is required 76 degree. Okay, joule per mole per Kelvin. Okay, and whenever it is commercially, it was 83, or particle size was smaller from 86. Okay, so this type of variation will be there. So this type of variation will be there. Okay, and that will be varied with heating rate. Okay, let's say certainly in the summer, temperature heating rate is very high. And winter, there will not be any heating rate. So degradation of your waste materials will be different. Okay, if you use them for the environmental purposes. So that is the reason to show the degradation at different heating rate. Okay, fine. So this different model have been used for different purposes. Now you see that samely the other method we have verified. Okay, a similar evidence as giving. Okay, the similar type of changing the activation energy, kinetics. Okay, the degradation, order of degradation, that also will be changing. Okay, these are common actually. Okay, now we can go to the final methods where the three heating rate techniques has been used. Okay, now you see that LNQ heating rate versus 1/T in Kelvin has been plotted. 5% conversion. So at a temperature, whenever you will be heating, there will be change of mass. How much percentage of conversion will be there? How much percentage of conversion will be there? Okay, you see, a different heating rate, conversion rate will be different. Now you see different particle size, they will be shifting. So at different particle size, so also their conversion from mass conversion for the after the degradation also will be there. Because whenever the particle size will be smaller, okay, their arrangement will be different and degradation also will be different. Rate constant, let's say rate constant. Okay, so rate constant, okay, 5%, 10% to 25% with, let's say, 500 nanometer particles. So they will be changing in the rate constant. Means whatever the degradation will be there, their degradation also will be different. Now we see that how much time we will be taking. Degradation percentage of time with particle size. If you see that there is clearly difference is observed of the thermoplastic polypropylene, which is a bulk commercially available, and with the change of the particles. Okay, so with change of the particles, degradation will be different. Now rate constant for the degradation, okay, for the polypropylene. You see that this is for 500 and this is for the different sizes of particles. So you see that, okay, so rate constant is very high for the degradation for the nano sizes particles with respect to the bulk or macro sizes of particles. So you can assume that whatever the polyethylene sheets are available, polyethylene bags are available, their structure, their arrangement of the chain will be different, and their behavior with response with change in the temperature also will be different. Okay, keep in mind all these things. Now see, what kinetic results are telling the polypropylene conversion rate whenever 5%, then you need this activation energy 90 degree, and whenever you need 60%, you need 186 kilojoule per mole or per grams per mole here. Okay, here. And nano size cases, you see that. Okay, nano size cases, if you see the 20 micron, nano size cases, you see how much increase for 5% conversation 90 to 98, but for 60% conversation from 186 to 204. It change. How much? Almost 20 kilojoule increase in activation energy for the degradation was occurred, and diffusion constant also changing. Okay, now see, clearly in going estimation of lifetime for the polypropylene, you see that. You see different plots are there here, lifetime versus temperature plots are there here. I have mentioned in the form of degree centigrade. Okay, now see first the blue one 5 micron sizes of particle. You see at lower temperature it can degrade. Okay, let's say at lower temperature, let's say again, how much time it can be there in the environment? 1 into 10 to the power 7 hours. You can convert it. How much year will be there? Almost it will be 100 years. Or 1000 year will be there. So a particle, polypropylene of 5 micron, if you heat it around, let's say 10 degree centigrade temperature constantly, then it can be there in the environment almost 1000 years. Okay, 1000 years. Now, let's say 500 nanometers particles, if you heat it 100 degrees centigrade, okay, if you see that 100 degrees centigrade temperature, if you heat, then come. How much? It will be there almost in be 1.25 into 10 to the power 7 hours, which is again almost more than 1200 1250 years almost, man, or 250 years increasing the stability. So stability will be there almost 250 years much more with respect to the bulb. Okay, so it is clearly visible that whenever you will be making reprocessing of your polymers, whatever the waste will be there, their lifetime can be increased. Okay, thermal stability lifetime can be there. Conclusion: single step decomposition is observed in the nitrogen atmosphere. Thermal stability of PP particle initially decrease and then increase as a particle size further decrease to nanometer scale. Activation energy, okay, degree of degradation or diffusion constant value are also particle size dependent. The value of kinetic parameter significantly controlled by the heating rate and calculation techniques. Kinetic result agree well with different models. Lifetime also depend on particle size. Most of the cases it has found that smaller particles will have much more. Now, I will be going for P directly. You see that from 461 to 465 increase the in the heating rate unit, and if you heat it 15 degrees centigrade, okay, also. Now you see with different the particles how it's now directly go to the lifetime. Okay, lifetime. So polyethylene, you see that red is showing for the 20 micron, and in green you see that this green is seeing, okay, 500 nanometer size. Now it has been calculated in year. Okay, so if you take the polymer particles of 500 nanometers and if you heat it around 110 degrees centigrade, then if you see that 110 degrees centigrade, you continuously heat it, which is below the melting temperature. So below the melting temperature, then these polymer particles can stay in the environment. How much year? 3.5 into 10 to the power 12 years. So these polymer particles can withstand 3.5 into 10 to the power 12 years. Okay, you see that why in the environmental pollution cases, okay, using of the polymer thin sheet is prohibited in the market because they will block this ways, they will not degrade, they are not biodegradable. Okay, they will take 10 to the power 12, 3.5 into 10 to the power 12 years to degrade. So we have to be very cautious. Okay, the P nanoparticles are highly stable and it is comparable to micro and micro size particles. Okay, so you see that how much stability will be increased. Similar cases. Okay, forget about this. The polystyrene also we have checked. So polymer particles, if you convert it, whatever the OS will be there or bulk to nano, there will be lot of changes will be there inside this. Okay, physical property, mechanical property, thermal property will be changing. Their surface property will be changing. Okay, if you make properly, less surface roughness you can make. You have to have better prospect to use in various purposes. Okay, so that is this thing. Nanopolymer highly crystalline. You can make highly crystalline. You can make it highly crystalline. You can increase the gas transition temperature. You can increase the mechanical property. You can increase the elastic modulus value. The particle size dependent, thermal degradation kinetics also you can increase. Okay, so these are these. Okay, so I will be telling that this work entirely I have done a long back. Okay, long back, at least 15 years back we have shown that why the nano size particles are giving this and the higher stability and what can be the reason for that. Okay, so I have done all these things. My PhD supervisor is Kamal Krishnakar. Okay, IIT Kanpur. All this work I have done in IIT Kanpur. Okay, I'll be very much thankful to them. Okay, all these things. Lot of references will be there. At least 17 reference will be there. And you can get all the detailed study of this. How we will be doing waste management. Okay, how we will be doing waste management. A lot of things there. Okay, and finally I will be thank to all for listening to me. Thank you very much. I have finished early. Okay, is there any question?
Thank you very much, sir. The session is now open for interaction.
I can spend at least. I have some meeting. I urgently have to go. go, but I can spend another 5 minutes.
Yes, sir. We will end by 11:30 sharp, sir.
Okay.
7 minutes, sir, dear.
Okay. So I am stop sharing and then can take the question face to face. Any question? Any question from the audience?
Sir, I have one question actually, sir. I
Yes.
want to know about the lifetime of plastics, polymer nanocomposition, how it can be different materials. I think if we fill by different nano, will the life of the polymer or composites can be modified?
It can be modified. It can be modified through crystal structure, entanglement, their arrangement. Okay. Whenever the arrangement and everything will be different, their degradation will be different, their movement will be different, their entropy will be different. Entropy is related to the degradation and other things, crystal structure. And their lifetime will be different. Lifetime here mentioned the lifetime for the degradation. And we have studied this from the thermogravimetric analysis, TGA. Lifetime you can calculate from DSC also.
Yes, sir.
Any other question?
Sir, there is one question from an offline participants. He wants to ask you.
Yeah.
Sir,
Hello, sir. Sir, how can we know the material is amorphous or crystalline in nature?
What is the question? Can you repeat it?
How can you know that the material is amorphous or crystalline in nature?
You can first checkpoint will be XRD. By XRD you can get it. If it is crystalline, then sharp peak XRD peak will be there. If it is amorphous, then AMP will be there. Same you can get it from DSC also. If your materials is completely amorphous, you will not get any melting peak. You only you will get the inflammation, okay, or fluctuation of DSC plot for TGA, glass transition temperature. Otherwise, it will giving the melting peak.
Thank you, sir.
thank you very much, sir. Thank you very much for this informative session, focusing in details of polymer, then different potential applications of nanopolymers, polymerization, materials for synthesis, process standardization, the elaborate talk on the kinetic model, which is people can, all of us, able to know about the inherent properties of the how the things can be modified or how the things can be changed, and about the lifetime, which is also most important for dealing with the waste related to the polymer. We are thankful to you, sir, and I, on behalf of CIPET CSTS-GUWAHATI, thank you very much for spending your valuable times and giving us such a nice and informative session, sir. Thank you so much,
Thanks
sir.
a lot. Thanks a lot. Thanks, Dr. Jyotika, to you and your team. Okay. Nice to talk to you all. If you have more questions, you can just drop me an email. Okay. I will be happy to address them. Okay.
Yes, sir. Yes, sir.
If
Thank
no
you,
question is there, quickly I will be will be logging off. Okay. I can log off.
Yes, sir. You can.
Okay. Then thank you very much. Thanks. Bye. Bye. Have a nice day to all. Bye. Bye.
Yes, sir. Yes, sir. So dear participants, now tea break will be there, and at 12 p.m. we will meet again with a talk on single-use plastic and waste management by Ambika Joshi of CIPET IPT Raipur. So participants can be at the same line or they can rejoin again at 12. So I request all of you that please do not get late and try to attend all the session, as 80% attendance is also mandatory, and how to manage waste, that is also important for all of us to know. So now tea break is there. So at 12 we will meet again. morning, ma'am.
Morning, ma'am.
Yes, we are going to start, ma'am, by 2 minutes.
Okay, it will take 5 minutes to start.
After 2 minutes, ma'am, we will start, ma'am.
Okay, okay, okay. Share करती हूँ।
A very warm good morning to all of you, my dear participants and resource person. Now we have with us Ambika Joshi from CIPET IPT Raipur. So before starting the session, I just want to briefly introduce ma'am with all of you. Ambika Joshi is presently working as a senior technical officer and the testing in charge at CIPET IPT Raipur. She has experience of more than 15 years in the domain of polymer. She has a vast experience in the area of plastic engineering and polymers. Before joining CIPET, she has also worked as a project assistant in National Physical Laboratory, New Delhi, and expertise in working on conducting polymers. She has completed her MTech in Chemical Technology with specialization in polymers from PTU Jalandhar. And also she is pursuing her PhD from NIT Raipur. Today, ma'am, will share a session on single-use plastic and waste management. We welcome you, ma'am. On behalf of CIPET CSTS-GUWAHATI, we welcome you for the session, ma'am. Over to you, ma'am.
Thank you, ma'am. I am very grateful to CIPET Guwahati for giving me this opportunity. So, I also welcome all the students and participants who are here to attend this lecture, a short lecture on single-use plastics and plastics recycling. So, I'll be just giving an overview about the plastics recycling and single-use plastics. I think my screen is visible to you. Screen is visible?
Yes, ma'am.
Okay. Okay, so I'll be starting my presentations on this topic of plastics recycling and single-use plastics. As we know that plastics is a wonder material, and just a brief idea I would like to give about the plastics recycling, that what is the need for recycling, because today it is a burning topic, and all over the world so many sanctions have been imposed on the use of single use plastics, and so much of emphasis is also given on plastics recycling and use of plastics in use of plastics and its disposal of the plastics in a proper manner. So much of work is being done in this field. So just I would like to highlight some of the major steps which have been taken by the government in this field. So first of all, I would like to give a brief introduction about the plastics, what are the plastic materials and how they are related with our day-to-day life. So as we know that plastics is a wonder material, and we cannot just assume our life We cannot just expect our life without the plastics. As soon as our day starts, we are surrounded by uh, so many things that are made up of plastics, and unconsciously or consciously we are using these plastics in our day-to-day life. So no wonder that plastics has its own advantages. It has a lot of advantages. That is why it is being associated with our life so well. It's low weight, it has high strength, it is durable, it has easy manufacturing techniques, it is economically feasible, it is versatile in nature, and it's durable also. So all these qualities makes it a wonder material, and makes it very efficient material, so that it gets connected to our day-to-day life. So a brief classification, as we all are from plastic field, so we are aware of all these things, but so many students and research scholars and other persons have also joined these, as madam has told. So I would like to give a brief this categorization of the plastics, how the plastics are classified. Broadly, it is classified into two categories: thermoplastics and thermosets. Thermoplastics are the materials which can be recycled, and thermosets are the material which we cannot recycle because of the presence of their 3D structure and cross-linking among the molecules. That is why we cannot recycle the thermoset materials. So whenever we are talking about the recycling, we are mostly talking about the thermoplastic materials only. So as you must have seen, these are the recyclable codes. These are the recycling codes for different kinds of plastic materials. Different kinds of plastic materials have different properties. They are associated with, and these properties are associated with the different chemical structures of our polymeric materials. So according to their functional groups, and according to the chemical structure of the polymers, they are used in different applications, and they have different properties. So the most of the plastics that we are day to day life we are using are the commodity plastics and some of the engineering plastics. Like PET is one of the material which is used for soft drink bottles and water bottles. Whatever water bottles we are using, they are made up of PET. HTP material is also used as a commodity plastics for water, juices, cosmetics, shampoo dishes, laundry detergent bottles, retail bags, then cereal box liners. Then PVC is the material which are used, which is a very versatile material, and it is used in making of toys, shampoo bottles, medical tubing, wire and cable insulations, films and sheets, construction products. Then LDP material is another grade of polyethylene, which is more flexible, and it is used for as a film. We are using it in different applications of frozen food bags, squeezable bottles. Then PP is the polypropylene materials, which are used for basically mostly used for medical bottles and medical whatever in medical field, whatever plastics we are using, it is mostly made up of PP material, polypropylene material. Then PS is one of the materials, that is the polystyrenes, which is transparent materials. It has very good transparency, and they are used for decorative items, for compact disc cases, food service applications, and grocery store meat trays, egg cartons, cutleries, cups, plates. So these are some of the recycling codes which you can identify on the back side of the some of the plastic materials. If you see, you can see this triangular shape and the number inside it. So इस number का मतलब होता है that it is made up, it is a code. If it is 2, then it is clear that it is made up of HDP material. If it is 3, then it is recyclable and it is made up of PVC material. If it is 5, it is made up of PP material. So we can easily identify the materials from which these are made, and they can be recycled. So these are the recyclable codes. So as we know that plastics is associated in each and every fields of our life. So if we see the data and we analyze the data, then we can easily see that plastics, they are used for more than 50%, more than 60% of the plastics are used in packaging sector. More than the 60% of the plastics is used in the packaging sector. Okay, either it is flexible packaging, or it is rigid packaging, or it is consumer packaging, whatever it is, but more than 50% of the plastic materials are used for packaging applications. Then other fields are like agriculture, constructions, toy sector, furniture, sports and leisure, housewares, electrical applications, and others. So, what are the broad areas in which plastics are used? Are agriculture, aviation, telecommunications, building constructions, electronics, medical, automotive, packaging, and infotainment. Then, if we see towards the global scenario, so we can from the data, as it is clear that plastic waste is a global phenomenon. Whenever you are using the plastics, the disposal of the plastics is also important. If we are using the things, it is equally important that how the things are being disposed. So in today's scenario, the problem is the disposal of the plastic waste is not proper, which is creating a hell lot of problems. So according to the data, we can see that plastic waste, it is a global phenomena. Over 8.3 billion tons of plastics has been produced since 1950, and about 60% of that has ended up in landfills or in natural environment. Only 9% of the plastic waste ever produced has been recycled, and about 12% has been incinerated. Incinerated means it is burned to ashes, while the remaining 79% has accumulated in landfills, dumps, or natural environment. Plastic waste, whether in a river or ocean or land, can persist in environment for centuries. Hence, by 2050, the amount of it has been estimated that if this plastic waste disposal is not properly maintained, then by 2050, the amount of the plastics in the seas and the oceans across the world will be more than the aquatic life. It has been estimated that if the scenarios remains the same, and no strict actions has been taken about the proper disposal of the plastic waste, then by 2050 the amount of the plastics in sea and oceans will be more than the aquatic life. So the plastic, these data show that what is the rate of plastics consumption in India. India recycles about 60% of the total plastic waste, and 70% of which is recycled at registered facilities, and 20% is by unorganized sectors, and 10% at home. So India recycles 38% more plastics than the global average of 20%. So according to the CPCB, which controls all the regulations of the about the plastic waste management and plastic waste disposal, that is the Central Pollution Control Board, it manages all the rules and regulations. So according to CPCB, India generates close to 26,000 tons of plastics a day, and over 10,000 tons of plastic waste remains uncollected because of the unorganized sectors and unorganizations. The plastic waste, it remains uncollected. So according to the FICCI study, the plastic processing industry is estimated to grow to 22 million tons. So now it has been estimated that the plastic industry will grow at a very high rate. And according to that, when the plastic industry will grow, then usage of plastics is growing day by day. Then the plastic waste which is generated will also be very high. So it is the need of this hour that we have to take certain big steps to manage the plastic waste which has been created and which will be created by the growing estimation of the plastic industries. So India's per capita plastic consumptions of less than 11 kg is nearly a tenth of the United States of America, but still we are unable to manage the things. So So it has become a plastic mess. As you know, the plastic industry uh, is growing day by day, and it is enormously growing in each and every field. So the plastic waste generation has become a big mess. Now, CPCB report shows India's plastic generation numbers are erroneous. The five takeaways from the recently released report that highlights the grim reality of India's plastic crisis is that why this is a plastic mess, and there are certain reasons for it. What are the reasons? The reasons are that India's total plastic waste generation is still it is an unanswered question. Then Mayor 14 of 35 India's state pollution boards, it submits partial information on plastic waste management. Then unregistered plastic manufacturing units are running, recycling units are running in the states, inadequate guidelines for plastic carry bags, and no state level monitoring committees. This is the most important point, that no state level monitoring committees are there to oversee the plastic management rules. So these are the reasons why the things are not being managed at the different levels. So these are the different fields from where the plastic waste is generated, like biomedical waste, packaging waste, electronic waste, automotive, agricultural, and plastic waste. Now, impact of the plastic waste. If the plastic waste it is generated in a huge amount, then it has impact in our day-to-day life, and it has impact on each and every sector of life, you can see. So what are the impact of the plastic waste? First is the economic losses. The places where tourism is the main revenue generation uh, system, then at that places if plastic waste is created along the shorelines, then it has a negative impact on the tourism sector. For example, Andaman and Nicobar Islands are under the plastic threat and facing the aesthetic issue because of the international dumping of the plastic waste. Then it has implications for the animals. Plastic ingestion upsets or fills up the digestive systems of animals and contribute to their death. Marine animals can also be trapped in the plastic waste, and they are exposed to predators. So it disturbs the food chain also. The plastics may also contain toxic animals which can harm the animal's vital organs or biological functions. Now, for human health, also we can see the chemicals which are released from the plastics. It contains compounds, very harmful compounds which are anti-androgen, bisphenols, and phthalates, and it has impact on the human health, leading to various hormonal and genetic disorders. These chemicals can interfere with the functioning of the endocrine system and thyroid hormones, and can be very destructive to women of reproductive ages. So directly it affects the endocrine system of the humans. Then it creates the land pollutions also. Plastics, it leach hazardous chemicals on land. It results in the destructions and decline quality of the earth's land surface in terms of use. Then it creates air pollution also. Plastic burning releases the poisonous chemicals into the atmosphere, impacting general well-being and causing the respiratory disorders among the living beings. Then ground, it also creates the groundwater pollutions, the leaching of the chemicals. It and it creates the toxic elements into the aquifers and water tables, indirectly affecting the groundwater quality. Then it creates water pollution. Many lakes and oceans have reported alarming cases of plastic debris floating on the water surfaces. Then interference with the food chain, directly or indirectly, if it is consumed, the harmful chemicals which are being consumed by the aquatic life, and indirectly we are uh, humans are also consuming those aquatic animals, then it enters in our food chain also, and then it can uh, be very harmful to our endocrine systems. So it enters the food chain and creates ingestion plastics, and it can create a very harmful diseases. Poor drainage systems, then drainage system is also clogged by the plastic bags and films, which causes the flooding. Then impact on the habitats. Sea floor plastic waste sheets could act like a blanket, inhibiting the gas exchange and leading to anoxia or hypoxia in the aquatic system, which in turn adversely affect the marine life. Invasive species, it can also lead to the potentially increasing the range of certain marine organisms or introducing the species into an environment. This in turn can subsequently changes the ecosystems of the region. So these are all the ill effects of the plastic waste. So if we see about the decompositions of the plastics, now these whatever right now we have seen is about the impact of the plastic waste in each and every sector of life. So, if the plastics are decomposed into the environment, then what are the decompositions of the plastics waste? It contributes to approximately 10% of the discarded waste. In the municipal solid waste, the contribution of thermoplastics is 80% because it can be recycled, and thermoset constitutes about 20% of plastic waste. Plastic waste is mainly decomposed in landfills where it may take up to thousands of years to decompose. This is the main reason why so many organizations and NGOs are also compelling the lesser use of the plastics. But use of plastics we cannot ban, but the use of such plastics which are creating the landfills and which are leading to the plastic waste which is not decomposed properly, that is the main problem. So plastic, it requires higher energy ultraviolet lights to break down. So the amount of the plastic waste in our oceans is steadily increasing. Its degradation takes much longer as a result of saline environment. So in short, we can say that decomposition of the plastics, it is a very difficult task and it takes thousands of years to decompose. Now, if we see, there are three major forms of plastics: micro, macro, and megaplastics. This we can see, these are the microplastics, macroplastics, and megaplastics. So pollutants, what are the major pollutants if it is decomposed we get from the plastics are the PVC when burnt results in emissions of deadly poisons named dioxins. Dioxins are highly persistent compounds with potential to become increasingly concentrated in living tissues as they move up the food chain. So PVC is used in making of toys, then PVC is used for a number of applications. We are using PVC as it is a versatile material. So if it is not disposed properly, then what are the harmful chemicals it eliminate are emission are out from the PVC are the dioxins, which are highly toxic chemicals. Then bisphenol is a chemical found in hard plastics and the coatings of the food and drink cans, water bottles, medical devices, household equipments, etc. Then it is an endocrine disruptor and a substance which interferes with the production, transport, and secretion of the natural hormones. So the highly toxic chemicals which are emissioned out from the plastics, it directly interferes with the endocrine systems of the human body. Then there is a recycle. Why there is a need for recycle? Then recycling, it keeps the trash out of the landfill. So why there is a need for recycling of the plastics? As we have seen, there are so many toxic chemicals which are eliminated out if waste is not disposed properly. Then the reasons for the recycling of the plastics, what are the major reasons why the recycling is emphasized? Recycling, it keeps trash out of the landfill. It recycles, reduces our need for the new raw materials. We can use these materials, we can change the shape, we can change its form, and we can use the same things. Then recycling conserves the energy, it reduces the pollution, and it creates jobs. It also gives new job avenues to the uh, to the youth. Then what is basically recycling? Basically recycling is, it is the process of collecting the waste materials and processing them into new products. Turning the trashed waste into useful products is beneficial for both the community and the environment. The recycling process can be of three types, and each type includes three basic steps. So recycling is basically, it is the collecting of the waste, and it is processing the waste and changing its form in some another beneficial form. So basically there are three kinds of recycling. First is the mechanical recycling, which is a very common, mechanical recycling is very common in India. It is the most globally used methods of giving residues new usages is mechanical recycling. It is used to recycle plastics either obtained from industrial scrap or domestic or commercial disposals. These are mechanically transformed into new materials without changing their chemical structures. So we are not changing the chemical structures in mechanical recycling, but what we are doing, we are shredding or we are grinding the plastic waste into smaller parts. Then there are certain steps to it, like grinding, washing, separating different kinds of plastics, then drying, regranulating, and then compounding. So basically, this is the different steps in mechanical recycling. Such mechanically recycled plastics are used in making garbage bags. So the when it is regranulated and it is compounded, then it can be used in making garbage bags, floor mats, hoses, car parts, packages. Then mechanical recycling is widely used for basically polyolefins, that is the polyethylenes and polypropylene. So this is the most common recycling method which is being used in India, that the waste is collected, and then after collecting it, it is washed, it is shredded, it is separated, and then it is regranulated and compounded, and it can be made into different forms. Now, the another kind of recycling is the energy recycling. The method is used to convert the plastics into both thermal and electric energy. It's called energy recycling. It is burning of the waste to produce the energy in the form of heat, steam, and electricity. In this kind of recycling, what is being done when the plastic waste is um, thermally heated, then the energy which is being produced, that energies, it is used in the form of heat, steam, and electricity. Basically it is the change of form of energy. The process is done by leveraging through incineration, and the heat is released in the form of fuels. Plastic materials possess a very high calorific value when burned. Since the heating value of plastics is high, they make convenient energy source. So basically, this is the method in which the energy is transformed from one form to another. There are catalyzers in waste incineration plants to withhold the emissions of the energy recycling process. Reducing water and carbon dioxide upon combustion makes them similar to other petroleum-based fuels. So this is another kind of recycling. Then third is the chemical recycling. Chemical recycling is among all types of recycling, it is the most complex method. In this process, the chemical structures of the plastics are modified after reprocessing them. Here, the structures are modified. We are changing the chemical structures of the plastics. The final product is produced to be used as raw material in different industries. It can also be used as a basic input in manufacturing new plastic products. It is an expensive process and requires a large amount of plastics available. It is still in its early stages and is a complex process and requires great technology development still. Okay, so in this type of recycling, what we are doing, we are just changing the chemical structures of the plastics, and after changing the structures we are using it as a raw material for the industries. Okay, so in this figure we can very well see that it is different steps of the mechanical recycling is being shown in this figure. We can see inspection, then chopping and washing, separation by flotation, because all the polyolefins they float on water, they have less density, so they float on water. So whatever the plastics they float, these are separated out. Then it is drying, melting by heat and pressure, filtering to remove the contaminants. Then it is molten and extruded into fine strands, and then it is pelletized or regranulated. So these are the different steps of the mechanical recycling what we are using in India. Now, advantages of we look upon the advantages of the recycling. We can see that it is waste. It reduces the waste. It is the how we can manage the plastic waste. Then it conserves the energy. It saves money. It creates new jobs and generates revenues and provides a sustainable source of raw material to the industry. Okay, these are the advantages of recycling. So, if we see what are the major uh, what are the major issues regarding the plastic usage, is that in day-to-day life we are just so much we are in media also we are seeing this that the single-use plastics must be banned, and there should be some alternatives to the single-use plastic, because as we have seen that most of the approximately more than 60% of the plastics are used in the packaging sectors, and single-use plastics is one of the major sectors where plastics are used for packaging also and in other things also. So single-use plastics, the government has planned to ban all the single-use plastics because it is very difficult to recycle these single-use plastics because of some technological issues. And if it is not recycled, so what it does, it creates landfill areas. It creates big garbage houses. It creates water clogging, drainage clogging. So all these issues are there if the single use plastics are not disposed of properly. तो सिंगल यूज प्लास्टिक्स होते क्या है बेसिकली, दीज आर द कॉमनली यूज्ड फॉर प्लास्टिक पैकेजिंग and it includes items intended to be used only once before they are thrown away. Okay, so single use plastics are disposable plastics meant for use and throw. So they comprise polythene bags, plastic drinking bottles, plastic bottle caps, food wrappers, plastic sachet, plastic wrappers, straws, stirrers, and styrofoam cups or plates. These are the general single-use plastics which we are using in our day-to-day life. and we all are very familiar to it, because these are the use and throw plastics. Once we use, we just throw it away. So it is a cheap and convenient that it has replaced all other materials from the packaging industry. But it takes hundreds of years. The problem is that it takes hundreds of years to disintegrate. So it is a huge problem. If we look at the data, out of 9.4 million tons of plastic waste generated every year in our country, 43% is the single-use plastics. Now, single-use plastic products are the water bottles, pouches, spoon, forks, glasses, plates, carry bags, wet wipes, personal and domestic use, fast food containers, sandwich wraps, hot salad boxes, beverage bottles, liquid refreshments, bars and wine bottles, medicine packaging. All these are single-use plastics. So these are the most common plastics which are being, which we can see here and there lying on the streets, on the beach areas, in the oceans, in the tourist spots and all. So the main polymers which are used in the production of single-use plastics, we can see that these are the different plastics which are used for SUPs, like PSE 6.7%, polystyrenes we are using 7.4%, is PET, which is used for making the bottles, soft drinks, juices. Then 7.5% are polyurethanes, 10% of the single-use plastics are made up of PVC, which is which includes window frames, floors, wall covering, pipes, cable insulations, garden hose. Then 12% are SUPs are made up of HDP. Then 70.5% are the SUPs which are made up of LDP and LLDP, which are the reusable bags, which constitute a major part of the SUPs. Reusable bags, trays, containers, agricultural films, food packaging films, etc. Then 19% of the materials are the PP materials, food packaging, sweet and snack wrappers, hinged caps, microwave proof containers. Then others plastics are also used. So basically you can see that most of the single use plastics are made up of polypropylene and LDP and LLDP materials, and HDP if we also include. So we can see that most of the SUPs are made up of polyolefins, HDP and that PE and PP. Okay, so this is the small categorization where we can see that what are the different SUPs which are made up of different kinds of plastics. Now there are certain advantages also of single-use plastic, that is why it is majorly we are using in different sectors. It prevents the spread of infections. Instruments such as syringe, applicators, drug tests, bandages, and wraps are often made to be disposable. Also, single-use plastic products have been enlisted in the fight against food waste, keeping food and water fresher for longer and reducing the potentials for contamination. So these are the certain advantages of the single-use plastics, why it is being used in a huge numbers. We are using the single-use plastics, but the problems are that they are the petroleum based products, they are not biodegradable. If we replace these SUPs with some biodegradable material, or with some material which can be easily um, disposed of, which can be disposed of in the environment easily, so that will be a very that will be a great help to the environment, as well as for the uh, all kind of problems that we are facing by the use of these, by the lack of the proper disposal of the single use plastics. So the problems are that they are not biodegradable and usually goes into a landfill where it is buried or it gets into the water and find its way into the ocean. So the main problem is that the disposal of SUPs is not proper. In the process of breaking down, it releases the toxic chemicals, additives that were used to shape and harden the plastics, which makes their way into our food and water supply. So the main problem, the zest of the problem is that SUPs that we are using, they are not properly disposed. And the problem is the disposal of this material, which is creating so much of havoc and mess, and in this mess all kinds of different plastics which are used for different applications we are targeting. Everybody is targeting plastics into it, that plastic should be banned, plastics are not good for the environment, plastics are this that. But the major issue is not the use of the plastics, the major issue is that disposal of the plastic waste is not proper. Okay. So concerns, what are the major concerns in this field is that less recycling. Only about 8% of the plastic gets recycled in the US. It is far cheaper to make things out of newly produced plastics than from recycled plastics. Recycling is not proper. Then limited efforts. State and municipal governments have had success in banning certain items like plastic grocery bags, foam cups, and drinking straws. But the efforts focused on the curtailing the production of SUPs have been limited so far. The ban has been imposed, but no such good alternatives have been given to the people so that they can stop the use of the SUPs, and in place of SUPs they can use the better alternatives. So advocacy efforts to persuade the consumers to use less plastics have failed to gain the traction. So this is why the efforts which are being put by the municipal governments are not a great success. So global initiatives are also there, and Indian initiatives are Indian government in a bid to free India of SUPs by 2022 had laid out a multi-ministerial plan to discourage the use of the SUPs across the country. So India has taken this initiative and it has planned it in a step-by-step manner by the plastic waste management rules that India will get rid of the SUPs by the 2022. Plastic waste management rules 2016, it was implemented 2016, which extended the responsibility to collect the waste generated from the products to their producers and brand owners. Now again the rules have been revised, and the India has planned to get rid of the SUPs by the 2022. By the end of this, the Indian government is planning to phase out SUPs to complete elimination, but concerns revolve around the availability of the alternatives in plastic waste management systems. The higher authorities in the government, they are planning to get rid of the SUPs, but they are parallelly, they are looking forward for the availability of the alternatives and about the plastic waste management systems as well. A government committee has identified the SUP's items to be banned based on an index of their utility and environmental impact. In the three-stage ban, the first category of SUP items proposed to be phased out are plastic sticks used in the balloons, flags. In first, as I have told that it is a three-stage process. So in first stage, it has been planned that sub items like ice cream, candies, and earbuds, thermocols, decorative items, sticks, balloons, um, they'll be banned. Then in the second category, proposed to be banned from July 1 includes items such as plates, cups, glasses, cutlery, forks, spoons, knives, straws, wrapping and packing films used in sweet boxes, invitation cards, cigarette packets, stirrers, and plastic banners that are less than 100 microns in thickness. Then in third category, a prohibition is for non-woven bags below 240 microns in thickness, and it is proposed from September next year. So, what are the impact of the SUPs on environment? It is the burning of the plastic waste releases toxic gases. Plastic waste dumping contaminates soil, water. Cows die due to ingestion of plastic waste. Littered plastic waste give ugly look and choke the drains. It produces very highly toxic chemicals which are commonly used as additives in plastics. Now, here we can see the impact of the single-use plastics on the environment, how the rivers are being polluted completely by the SUPs on the beach sides. Then the animals are being killed due to the ingestion of the plastic materials. Then soil or landscape degradations due to the plastic litter, open burning of the plastic waste causing toxic chemicals and producing air pollution. So all these are the impacts of the SUPs. Now, why it is a mess? Because of the people's negligence. People are not aware of their surroundings. The large presence of SUPs in the environment is symptomatic of poor or failing waste management systems. Single-use plastics end up littering the environment in part because of irresponsible individual behaviors. Then poor waste management systems also play an enormous role. So majorly, people are not aware about their surroundings, about the plastic waste management systems, and about the proper disposal of the SUPs. Now, there are certain alternatives to the use of SUPs which we can implement at each and every level, like devising the feasible alternatives for SUPs and targeting the consumers and retailers for better marketing. So, if some alternatives are there, it should be properly marketed and it should reach the consumers. Also, a thorough analysis on the alternatives versus their carbon footprints should be it should be compared, and it should be awareness should be made to the people. And for instance, cotton bags sourced from virgin cotton, cooler cups, baked in cleans have higher environmental footprints than plastics. Then also options of giving enough time of transition to industry. So these are some of the alternatives which should be planned by the industries, by the authorities, so that they can be better in a better way. We can give good alternatives to the SUPs. In the present context, jute and upcycled cloth bags, bamboo and wooden cutlery, leaf-based plates, glass and metal containers are some of the immediate alternatives available. So these alternatives should be implemented, and industries should come forward for their manufacturing the products which are made up of these alternatives, like bags made of cloth bags, bamboos and wooden cutleries, leaf-based plates, glass and metal containers. So once they are being manufactured, they should reach to the markets. It should be properly marketed and it should reach to the consumers and the end users. So slowly, the awareness is also required. People should also be aware about that instead of using the SUPs, they can use the better alternatives which are available. Now there are certain pros and cons of the SUPs. It's every everything has its advantages and disadvantages as well. So the what are the alternatives we are using? They are somewhat expensive. Their environmental impacts are related to production and transport are significant. So slowly, it will step by step. It will be implemented and it will come into force. So initially it will be somewhat expensive, but slowly and slowly, if the government will support the things, then these alternatives can easily be implemented. Now, reusable bags can be the preferred alternatives. Then, Government of India and plastic waste management rules, they have framed certain responsibilities for all the local bodies and gram panchayats, because it is not a single person job. It is the responsibility of each and every level, from the local bodies to the gram panchayat levels to the single citizens, and everybody should, because everybody is the stakeholder in this system. So responsibilities have been imparted by to the local bodies and gram panchayats, that they will segregate the waste at the source, then channelization of the recyclable. First of all, the people have to has awareness should be there among the citizens, that they should create different bins for the dry waste and wet waste, and then these wastes are being collected by the Nagar Nigam authorities, and then they are segregated properly. Plastic waste is segregated by the local bodies and gram panchayats levels. They will and then they will channelize the recyclable plastic waste fraction to the recyclers, ensuring the processing and disposal on the non-recyclable plastic waste as per the guidelines issued by the CPCB, conducting awareness programs for the plastic waste management. The local body should set up for plastic waste management, then the local body to frame bylaws incorporating the provisions of these rules. So the local bodies, municipal corporations, and gram panchayats have been imparted these responsibilities, that they will channelize the proper disposal of the plastic waste. Then, what are the responsibilities of the waste generators? To minimize the plastic waste generation and segregation at the source, no spreading of the waste, and ensure the segregated storage of waste at the source. Every person responsible for organizing an event in open space which involves service of the foodstuff in plastics or multi-level. So, as a common citizen, the responsibility of the waste generators. Who are the waste generators? Common citizen, common people are the waste generators. So their responsibility is that they should, whenever they are using the plastics, they should segregate it at the source itself, and the no spreading of the plastic waste should, and ensure the segregated storage of the waste at the source. Then every person and people should make the awareness among the masses, among the surroundings, that there should be properly steps should be taken for the segregation of the plastic waste. So it should not be thrown here and there, and it should be properly segregated, or it should be properly stored. The plastic waste should be properly stored, so that it can be channelized and it can be sent to the local authorities for further processing. So today's waste is the tomorrow's resources. So if this kind of responsibilities are shared by each and every citizen, and by the local authorities, by the gram panchayats, by the state level monitoring committees. So we can see that we can reach up to the zero waste concept. So it starts from the door to door collection and the segregation, then the two bin system, wet and dry, then transportation and channelizing the waste, then utilization in the different sectors, then utilization in the different sectors is the recycling. Here we are talking about the recycling the products and using it in different forms, and then it can lead to the zero waste concept. So basically, if we follow all kinds of the rules and regulations, then the people are made, awareness is being made among the masses about the proper waste disposal, then at some point of the time we can reach up to this level of the zero waste concepts. So India is now turning its attention to the 10 single-use plastic products. Consumption reduction targets. Member states will have to reduce the use of plastic food containers and drink cups. They can do so by setting national reduction targets, making alternative products available at the point of the sale. At the point of the usage points, some alternatives should be have to be there, or ensuring that single-use plastic products cannot be provided free of charge. So obligations for the producers will help cover the cost of the waste management and cleanup, as well as awareness raising measures for food containers, packets and wrappers, drink containers, cups, tobacco products with filters, wet pipes, balloons. So these are the responsibility for the producers also. Labeling requirements. Certain products will require a clear and standardized labeling which indicates how waste should be disposed. So proper step-by-step procedure should be mentioned on the products, that how it should be disposed, the negative environmental impact of the product, and the presence of the plastics in the products. So these information should also be labeled accordingly, so that the people become more aware about the things which they are using. Awareness raising measures. Awareness raising measures. So member states will be obliged to raise the consumers awareness about the negative impact of the littering of the single-use plastics and fishing gears, as well as about the available reuse systems and waste management options for all these products. So common stakeholder groups are the national and stakeholders which are participating at all levels are the national and local government entities, national waste management authorities, local waste management officers, trade and industry associations, single-use plastic producers, retailers, individual citizens and organized civil society groups, then environmental NGOs. Now, if we take a look on the social engineering, is that the presently consumer awareness about the negative impact of the littering should be there, and reuse systems and waste management options for all these products are still limited. So this further needs to be strengthened through communications, strategic planning, consumer awareness campaigns should be there, raising business awareness, media outreach activities, cleanup campaigns, entrepreneur innovations, scientific research, constructive amendments in legislation and sustainability. These mechanisms will not only improve the eco consciousness among citizens but will also empower and encourage widespread actions. So way forward is the economically affordable and ecologically viable alternatives, which will not burden the resources are needed and their prices will also come down. Need to promote the alternatives like cotton, khadi bags. So consumers can also help by promoting the alternatives. More R&D is required to look for sustainable, viable options. Citizens have to bring behavioral changes and contribute by not littering and helping in waste segregation and waste management. Behavioral change is the major thing that that needs to be uh, implemented, or it needs to be there in all the responsible citizens of the country, where if it behavioral changes are not there, people are not changing their behavior, then it is very difficult to come across this problem, because behavioral change is a must. Whatever the alternatives are there, whatever the implementations are there, whatever the rules are there, if we are not following those rules, we are not changing our behavior towards the society, then we cannot reach up to the level what is being what the goals has been set by the um, by all the local authorities and state government municipal corporations. So behavioral change is a must. Raise the awareness, people should have awareness. And how we can raise the awareness among the masses about the proper disposal and the plastic waste management is that by educational programs, by workshop, by creating workshops, by workshops in schools, extensive multimedia awareness raising campaigns, door-to-door campaigns, development and distribution of the information materials, showcasing, distributing the alternative options to single-use plastics. So if this kind of awareness is made, then it will lead to the behavioral change, and once the behavioral changes are there, the problem can be sorted out easily. So solutions, what you can do is social and behavioral changes, technological development should be there. All these things should go hand side by side and hand by hand. All these things should go side by side. Social and awareness should be there, technological developments, regulations and awareness. If all these are being done at each and every level, then we can spread the awareness and the idea that we can change the consumer culture. We can educate the people for these things and we can make a difference. So something everyone can do is reduce, disuse and recycle. So I thank you for this patience hearing about the single-use plastics and the plastic waste management. Thank you, ma'am.
Thank you, ma'am. Now the session is open for interaction.
Yes.
So I request online participants their hands if they have questions, and we have offline participants also have some questions.
Hello, ma'am. Good afternoon, ma'am.
Yes.
Ma'am, I would like to know about thermosetting resin, that whether the unsaturated part or the saturated part is responsible for resin formation.
Sorry, please be louder.
Ma'am, I would like to know about thermosetting resin, whether,
Thermosetting resins, yes.
yes, ma'am, whether the unsaturated part or the saturated part is responsible.
Actually, it is the unsaturated part because the thermosetting polymers, they are cross-linked by some cross-linking agents, and it is very difficult to break those bonds. Okay, what
Okay, ma'am.
happens when we heat the thermoplastics? What happens? The bonds are breaking. Okay, so when the bonds are breaking, it is changing its shape, it is becoming liquid, and it is coming in molten state, and at that time we can reshape it. Okay, but it is the case is not the same with the thermoset plastics. In case of thermoset plastics, the thing is that they are cross-linked, highly they are cross-linked with the help of the cross-linking agent. So whenever we provide higher temperatures to the thermoset materials, instead of the breaking of the bond, what happens? It degrades. Okay,
Okay, ma'am.
so if it is degrading and it is not coming into molten state, then we cannot reshape it. No.
Yes, ma'am.
Yeah.
Ma'am, I have one more question.
Yes.
I would like to know about the cure of thermosetting resin. What
Fuel.
is it? How it is done?
What?
cure of thermosetting resin?
Pure.
Yes, ma'am. Cure, C-U-R-E.
Cure.
Curing
Curing.
of
It is a process. Curing is a process in which it is cross-linked. 3D network state is being, it comes into 3D network state. Okay, it's a chemical reaction in which the 3D network state is, the material is, is turned into 3D network state. Okay, there are certain chemicals which are known as the curing agents. Okay,
Yes, ma'am.
I hope it
Ma'am,
is clear. Yes.
yes, ma'am.
Huh.
Ma'am, I have one more question.
Yes.
About the reinforcing of fiber with a thermosetting polymer.
Mm-hmm.
Ma'am, whether how to enhance the quality by reinforcing the fiber?
How to enhance the quality?
Yes, ma'am.
See, here you are asking about something about the composite materials. Basically, these are the composite materials, and there are two parts of the composite materials: matrix and the reinforcement. Okay, so reinforcement is always there to strengthen the material. It is the backbone of the composite material. Whatever reinforcement is there, it can be glass fibers, it can be boron fibers, it can be in a particulate filler manner. So reinforcement is always there to strengthen the material, whatever form it is. Okay, the word itself, it is self-explanatory: reinforcement. Okay, so it is one of the major part of the composites along with the matrix reinforcement. Okay, so reinforcement is always there to strengthen the material, to give it a proper backbone. Okay.
Okay, ma'am. Thank you, ma'am.
Anything else?
thank you, ma'am.
Okay, thank you, ma'am, for giving me this opportunity. I hope this session was um, informative for the students and for all the participants who had a patience hearing.
And no, we have also able to learn many things related to single-use plastics and its rules. Because
Yes,
normally, if people are not from domain of plastics, they have less knowledge about how to manage the waste and what are the laws, how
yes,
to make committees, and how we can reduce and uh, give contribution to the cleanliness of the environment. We are
yes,
very
yes.
much thankful to you. And ma'am, there is another more questions from a participant.
Ma'am,
Yes.
I want to know about charging the properties of resin via chemical reaction. How actually it is done? And I don't know about. I need concept about this.
What you are asking?
Ma'am, how the charging is done of the
Charging?
resin,
Be clear.
charging the properties of resins. How to do it actually, ma'am? Charging the properties of
Means that he is asking about actually the mechanism of ionization
About
for
the
of resin related to cure of thermosetting resins. Ma'am, he is asking.
thermoset resins. You want to ask what about the thermoset resins?
Ma'am, it is about the charging of the properties of resin.
Thermosetting.
You better write it down, I think.
5:30.
I'm not getting your question.
Ma'am, can I give him your email ID so that he can ask the questions there?
Sure. Okay, charging the properties of thermosetting resin. Okay, you give your mail ID, I will send you the answers. Okay.
Okay, ma'am.
Okay, ma'am, I will share your email ID to the participants because since the
Sure.
session is very
Sure, I will
informative
share
and
it with me, the question also and this mail ID also. I will answer there. Okay.
yes,
Any
ma'am.
more
Thank you so
questions?
much for
Thank you, ma'am.
spending the valuable times
Thanks a
and
lot.
share this knowledge with us, ma'am. And many people has written in the chat box for this informative presentation. They thank you very much, and they are asking for me about the materials also, ma'am.
Okay, no
Because
problem. Whatever their queries are, I will answer it. Okay.
yes, ma'am. And the materials in your own way, ma'am. Please kindly if you send us this
How, what
summary of this
materials?
session. Thank you for this wonderful and great session. It is as I have said like this, and many participants has written in their chat box also,
Yes.
because really it's a very informative session regarding to the single-use plastic and how to manage it, and it is the need of the hour actually.
Yes.
I, on behalf of CIPET CSTS-GUWAHATI, thank you so much for spending your valuable time and sharing these knowledges and information with us, ma'am. Thank you, ma'am. Looking
Okay.
for.
Thank you, ma'am. Thank you. Okay.
You can leave, ma'am. If you want, you can leave the session. Dear participants, thank you very much for your kind attention and for consistent attendance. And we expect it for the another 4 days also. And in the second half, we have the live demonstration of processing department. But before that, a briefing will be there. So I request everyone to join the session at 2:30 p.m. After lunch break, we will meet again at 2:30 p.m. You can stay at the same line or you can rejoin again. Thank you so much. And if anyone has to ask anything regarding the attendance and any kind of things, you can ask me or you can write at the chat box also. A warm good afternoon to everyone. We are going to start by 5 minutes. A very warm good afternoon to today's resource person and my dear participants. We are going to start our session, post-last session. And as per our schedule in the post-last session, we have the demonstration of the processing lab. And since our course is in blended mode, online and offline, so our resource person, Jayanta Bussa, he is an experienced He has vast experience in the domain of CAD, CAM, and processing, and he has more than 10 years of experience in the processing department. So we are fortunate enough that he is with us, and before proceed for the demonstration of the processing lab for the offline participants, since we have the participants in the blended mode, so sir will try to just briefly introduce about the processes of processing and different techniques. Over to you, sir.
Thank you, madam. Good afternoon to all, my dear friends and colleagues. So, today we are going to start about the plastic processing techniques lab, where we are manufacturing the plastic products with different techniques by using different kind of material and machineries. We are going to manufacturing different types of products. So I am going to explain about the three basic processes which we are using in frequently in injection molding and compression molding and rotational molding and extrusion blow molding, which we are using frequently for manufacturing different type of plastic products. So I am going to explain all these 4 or 5 kind of machines. Now I am sharing the slides about the injection molding process. So injection molding is the basic process where we are making the manufacturing the plastic product by using different kind of machine. So here we can make plastic product like solid weight neck, flat products, bucket, cabinet, automotive products, and industrial part by injecting the plastic granules or plastic molten thermoplastic materials inside the mold cavities, inside closed mold cavities. So there are 3 types of injection molding machines. One is hand injection molding machine. Second one is plunger type injection molding machine. Another is reciprocating screw type of injection molding machines. So here we are showing that hand injection molding machines, how it is look like. In hand injection molding consists of barrel, plunger, band heaters, along with energy regulators, rack and pinion system for injecting the raw material by the plunger or a torpedo and a nozzles. Okay. In plunger type injection molding machine, there will be 2 types. One is horizontal type, another is vertical type. In horizontal type, plastic material we are putting in a torpedo, in a nozzles, and their plastic granules will be heated up and it will be injected inside the mold. And these are this reciprocating screw type of injection molding machine. Here there are 3 different types of zone, where feed zone, compression zone, and metering zone. In feed zone, what will happen that granules will come, granules we are giving to the hopper, then after that it will be push up to the next zone in transition zone. So in transition zone, what will happen? Plastic raw material will be compressed, and it will move forward for the metering zone. And metering zone, what will happen? That plastic raw material will be completely melted, and it will be gathered in the front, and then it will be injected inside the mold. So these are the machine components. This one is a hopper, heater, nozzles, some stationary platen, mold platen, reciprocating screw, and reciprocating screw, and barrel, injection chamber. There will be a screw. In injection molding process, the plastic raw material is plasticized by the reciprocating screw, and it will be injected the molten material into the closed mold via the channel of gate and runners. Then after that, we have pulled the mold and refill the material for the next cycle, and after that eject of the product. Then after again it will be closed the mold for a further cycle. These are the examples of injection molded part which has been manufacturing in different types of mold. This computer casing, then CD player, then this Xerox machines, part, freezer, cabinet. These are the automobiles, parts, different types of fittings, hair dryer, speaker, car, and these are the electronic devices which has been developed and manufactured by the injection molding process. Flame cover, lighter casing, combs, party tableware. So these all parts has been developed by the injection molding process. So what are the advantages? Here, lots of advantages has been found in the injection molding process. Some of them are parts can be produced in higher production rate, large volume is possible, relatively low labor cost as per the obtainable, process is highly suspendable automations, parts require little or no finishing, many different surface colors and finishes are available. Good decoration is also possible. For many shape, this process is most economical way to fabricate. And minimum scrap loss has been found in such as runner gates, and which can be we are again reused it. Same item can be molded in different types of machine without changing the machine or mold in some cases. Close dimensional tolerance can be maintained. Parts can be molded with metallic and non-metallic insert. Part can be molded in combination of plastic and such as glass fibers, talc, and carbons. Limitation of injection molding. So some limitation also it will be there for injection molding machines. Those are mold costs are too high. Then mold machineries and auxiliary equipments are costs also very much high. Lack of knowledge about the fundamentals of process cause problems. Lack of knowledge about the long-term properties of materials may result long-term failures. Now I am going to explain about the mold operation sequence, how it will works. First, what will happen in injection molding machine? The mold will closed and screw begin to move forward to the injection direction. Then after that, what will happen? If screw will move forward, then some material will also going to fill inside the cavity. Then after that, what will happen? The cavity will be packed as the screw is continuously moving. Then after that, what will happen? The cavity will be cools as the gate freezes off and the screw begins to retract to plasticize the material for the next shot. Next, what will happen? Once it will be cooled, that part has been ejected from the cavity. So again, that mold will be closed, and for the and again next cycle will be begins. So these are the basic operations which has been continuously followed in injection molding machine, and different products will get it by changing the mold. So what is mold? Here we are trying to explain the different types of part in the mold. So in molds, these are the necessary parts required for the for running the properly in the machines. So such as mold cavities, then core parts, back plate, riser, ejector pin, ejector rod, ejector assembly, then back plate, guide pin, guide bush. These are the necessary part for the injection mold. This is the typical mold triplet molds examples. So here one stationary plate will be, a platen will be there, then moving platen will be there. There will be a tiger. So the first one is we are showing that here it is the two plate where the two impression we are found, two parts we are found together. Runner also it will come. In triplet mold, what will happen? Runner will be ejected in differently and product will get it in differently. So feed system, here we are showing the last diagram. We are showing that there will be a proper with the feed system. We are showing that component also it will be attached. Here some port impression is there. Here gate, screw, main runner parts, force leg, branch runner also we are found, including it is known as the feed system. So next we are moving for the blow molding process. In blow molding process is widely used for making the bottles, hollow articles by using different types of machineries. The commonly used materials are PE, PVC, PET, PC, PA. This kind of material has been used for manufacturing the PET bottles or bottles. So in blow molding process, we can we are getting for the getting mass productions by rotational molding or injection molding. We are not able to achieve the bottle like structure, but in extrusion blow molding we are getting the large quantity of production by using the different types of machines. So these are the examples. These are the bottles which has been manufactured in the extrusion blow molding process or patch stretch blow molding process. So principle is material is feed into the hopper. Then after that the barrel will be heated and that raw material will be extruded out from the extruder. With the help of screw rotation and heater, the plastic is melted and homogenized. Then melted plastic will be forced to come out from the dies or hot paste tube. Then it will be taken out to the mold and it will be pinched off and it will be blown inside the cavity. So this is how the blow mold look like. Here hot perigon will come out and that perigon has been pinched off and it will be blown by the use of blow pin. And blow pin, what will happen that high air pressure will be blown inside the melted plastics. The basic requirements are homogeneous melt of the plastics, formation of the molten resin into the hollow perigons, sealing of the end of the perigon into the closing mold, except that throughout the blowing airs can be supplied. So this is the basics of blow molding process. Now we are moving for the rotational molding process. In rotational molding process, we are also making the hollow kind of products or hollow kind of particles. In what will happen in here, that plastic materials or plastic powder, it will be in a powder form, which has been the mold has been rotated biaxially during heating and cooling cycles. Rotational molded pieces are stress-free because pieces are produced without any external pressures. This process has capability for manufacturing around 3,000 gallons, and the last type of hollow containers or hollow plastic parts can be manufactured by this process. This process is required relatively expensive equipment, exerts only in small pressure on the material being formed. So here is the principle. So principle is that fine powder has become the molten and come into contact with the hot metal surface, and the mold is taken up to the shape of the surface. As the only female mold is used, the only pressure exert those induced by the gravity or centrifugal force. The polymer is then cooled and contact with the metal, which has been solid copy of surface has been manufactured. Rotational molding permits to make a wide variety of fully and partially closed items. So these are the examples which has been manufactured. This part has been manufactured in the rotational molding process. So this water tank, then buckets like structure, then these cabinets and everything is manufactured in the rotational molding process. So these are the loft tank and cylindrical vertical tank has been manufactured by the rotational molding process. So major advantages is that rotational molding compared to the other processes, very large part can be produced. It requires comparatively low cost input. The product is stress-free with the strong outside corners. There is no well lines, screw or gate marks. Impact toughness will be improved. due to the brittleness has been reduced, external dimension details can be achieved, and better surface finish also will get it. The color change of the product also made very easy, and similarly mold changes also can be done rapidly. Multi-layer mold also molding is also possible for providing chemical resistance and strength of the part. Good control over the wall thickness, and we can maintain the uniform wall thickness overall the part. And mold can be done with the metal inserts and minor undercuts. No scrap and very little scrap is produced. Low tooling cost. Disadvantage of rotational molding is longer cycle time is required for manufacturing the part. In case of bigger part, loading and unloading is very expensive. Labor cost is required more. The process is not suitable the part with a wall thickness of less than 0.03 mm. The conversion of the plastic granules is conversion of plastic granules to powder form increase the equipments and product cost. Limitations are it often the molding process and there is no course inside the hollow parts. Surface details and dimensions can be provided and controlled on the side or outside of the part. The process requires heating and cooling not only plastic materials but also molded as well. The long heating cycle increase the possibility of the thermal degradations. There is no suitable for material less with resistance withstand with long heat hot cycle. The material mass capable being pulverized into the fine powder that flow like liquid. Removal of the plastic stick into the surface of cavity, careful application of the mold releasing agents. So these are the limitations for the rotational molding process. So I want to to share the practical experience to the students in our plastic processing lab. So I am going to share some videos how the manufacturing process is going on in the plastic processing lab. Next one.
আৰু exit case কৰি দিম ন
এইটো নাই এইটো ভিডিও নাই Now, hello. Now I am going to show the another techniques for manufacturing the plastic parts. Rotational. Rotational. Thank you so much. Last time we have shown that rotational molding process. Now I invite our student to see the practical view, practically they can see and they can learn about the plastic processing lab in our processing department.
Thank you very much, sir. Thank you very much for giving this valuable information related to the processing and the videos also, since we have a live demonstration. As for the offline participants, now they will proceed for the live demonstration of the processing laboratory, and we have shown some videos so that all the participants can get the experience how the processing of any kind of techniques of polymer and plastic materials. And I expect that if time permits and if the situation permits, everyone can visit CIPET CSTS Guwahati, all the online participants too. Sometimes when they will get the time to our processing laboratory, as we have different types of laboratories. So, and if they have any questions, or if our participants can want to interact with our sir, they can raise their hand before proceeding for the live demonstration. If anyone has to know anything related to the processing techniques, the session is now open for interaction. Okay, now we will proceed for the live demonstration of the processing laboratory for the offline participants. So thank you so much. And online participants, please join tomorrow morning at 10 a.m. And we have at 10 a.m. we have the lectures by Dr. Nirmala Devi, and she will talk on utilization of plastic waste and its related technologies. So thank you very much. Online participants can leave the meeting for today. And there is another information for the participants. Since we are using the Cisco WebEx platform, meeting platform, so the attendance are recorded by the software itself. So at what time they are making their entry, how many times they have left the meeting, and when they have rejoined again, everything is recorded by our software. So there is no need to worry for the attendance. So for each and every session and for each and every individual, attendance is recorded by the software. Those who have already attended this type of meetings, our earlier meetings, they knew it very well. And those who are new to this first time, so for them itself, I am giving the information that the attendance is recorded by us, and it is not manually, it's by software. So thank you so much, and we will meet again at tomorrow morning at 10 a.m. So online participants can leave the meeting link, and offline participants are requested to proceed for the live demonstration of the processing laboratory. Thank you so much.